Mercury. There is something quietly wonderful about the night sky, about the way it stretches out above us, vast and still and impossibly deep, holding within it more mysteries than any one lifetime could ever fully unravel. And yet, for thousands of years, human beings have looked up at that same sky, the same darkness, the same scattered light, and found within it a sense of peace, a sense of belonging to something much larger than themselves. Tonight, we are going to slow down together. We are going to let the world grow quiet around us, and we are going to turn our attention gently, unhurriedly, toward one of the most fascinating objects our ancestors ever set their eyes upon. A small, ancient, endlessly surprising world that has been circling our sun since long before the first human footprint was ever pressed into the Earth. The planet Mercury. Before we begin, I want you to take a moment just for yourself. Let your body settle into wherever you are lying or sitting right now. Feel the weight of your limbs. Notice the rise and fall of your own breathing, that slow, automatic rhythm that your body maintains without you ever needing to think about it. In and out, in and out. There is nothing you need to do right now, nowhere you need to be, no task waiting at the edges of your attention that cannot wait a little longer. The only thing asked of you in this moment is to simply listen, and to let the words wash over you like something warm and unhurried, and to allow your mind to drift wherever they may carry it. We are in no rush. We have all the time in the world. So let us begin. Let us begin at the very beginning with a name. The planet we are going to spend our time with tonight is called Mercury. That is its official name, the name recognized by every astronomer, every space agency, every scientific institution on Earth. Mercury. It is a short word, only 3 syllables, but it carries within it an extraordinary amount of history. It carries the weight of ancient civilizations and mythological gods, of careful observations made by people who had no instruments beyond their own patient eyes, of questions that took centuries to answer. Say it slowly to yourself if you like. Mercury. There is something almost musical about it. Something that sounds, perhaps, like it belongs to another age, which, in many ways, it does. The name Mercury comes from the Romans. It was given in honor of Mercury, the Roman god of messages, travel, commerce, and speed. The divine messenger. The one who carried news between the realm of the gods and the world of human beings, darting from one place to another with a swiftness that no mortal could match. And the reason the Romans chose this particular deity for this particular planet is genuinely poetic when you sit with it. Of all the moving lights the Romans could observe in the night sky with their naked eyes, and there were 5 of them, the 5 classical planets. Mercury, Venus, Mars, Jupiter, and Saturn. Mercury, the planet, moved the fastest. It swept across the sky more quickly than any of the others, appearing in one part of the heavens and then, within just a few days or weeks, rushing off to another. It never seemed to linger. It was always in motion, always racing along the horizon, always hurrying on to wherever it was going next. And so the Romans gave it the name of their fastest god, the name of the one who was always running. Mercury. There is a kind of wisdom in that naming, a recognition that the universe has personalities in a way that different celestial objects move and behave differently, and that those differences are worth noting and worth honoring. The Romans didn't just label what they saw. They interpreted it. They looked at the sky the way one might look at a piece of music, finding not just notes but meaning. And the meaning they found in that swift, restless point of light was speed. Motion. The eternal journey. Mercury. Now, if you were ever to look at the astronomical symbol that represents Mercury, the symbol used in charts and scientific diagrams and old celestial manuscripts, you would find something quite elegant and full of its own quiet storytelling. The The symbol is composed of a circle, representing the planet itself, sitting atop a small cross, a traditional symbol of the earth, of matter, of the physical world. And rising from the top of that circle is a small crescent, curving upward like a pair of horns, or like a set of cupped hands reaching toward the sky, or, and this is the intended image, like a pair of wings. Because that symbol, that combination of circle and cross and crescent, is meant to depict the helmet of Hermes. Hermes, you see, is the Greek equivalent of the Roman Mercury. In Greek mythology, Hermes was the messenger of the gods, fleet-footed, clever, always moving, always carrying some important communication between the divine and the mortal worlds. And his most distinctive feature, in artistic representations, was his winged helmet. A helmet with small feathered wings attached to either side, symbolizing the speed and freedom of flight. That is the image preserved in Mercury's astronomical symbol. A helmeted, winged figure, captured in a few simple curves and lines, carrying within it the entire weight of a mythological tradition that stretches back more than 2,500 years. Every time an astronomer writes or draws that symbol, they are, in some small and perhaps unconscious way, connecting themselves to the ancient Greeks who first looked up at the sky and tried to make sense of what they saw. There is a beautiful continuity in that, a thread of human curiosity running from the ancient Mediterranean all the way to our most modern observatories and space missions. We are all, in our way, descendants of those first watchers. And speaking of those first watchers, one of the most remarkable things about Mercury is that it has always been available to us. No telescope required, no special equipment, no dark sky observatory, no scientific training of any kind. Mercury is visible to the naked eye. On the right evening or the right morning, in the right part of the sky, an ordinary person standing in an ordinary backyard can look toward the horizon and find it. A steady, unwavering point of light, slightly warmer and brighter than most of the stars nearby, and unlike the stars, not twinkling, just shining, calm and constant, low against the twilight. It is there. It has always been there. Every generation of human beings who has ever lived under an open sky has had access to it. And because of that, Mercury's history as an observed object stretches back further than almost anything else in the human record. The earliest documented observation of Mercury that we know of dates to approximately 3,000 years before the Common Era, 3000 BC, which means that people were carefully watching and recording Mercury's movements in the sky roughly 5,000 years ago. The civilization responsible for those earliest records was the Sumerian civilization, one of the oldest complex societies in human history, located in the region of Mesopotamia, in what is now the southern part of modern Iraq, between the great rivers of the Tigris and Euphrates. The Sumerians were extraordinary observers of the sky. Astronomy, or what we might more accurately call astrotheology, the study of the heavens as a divine language, was one of the central intellectual pursuits of Sumerian civilization. They built tall temple towers called ziggurats, and from the tops of those towers, their priests and scholars would watch the sky night after night, year after year, carefully tracking the movements of the stars and planets and recording what they found on small clay tablets inscribed with a wedge-shaped script called cuneiform. Thousands of these tablets have survived into our own time, and among them are records that clearly describe a wandering celestial object moving with unusual speed across the heavens. That object was Mercury. Close your eyes and imagine, if you like, what it must have felt like to be one of those Sumerian observers. Standing at the top of a great stone tower in the warm night air of ancient Mesopotamia, surrounded by a darkness far deeper and more complete than anything most of us experience today. No electric lights, no city glow on the horizon, just the pure, astonishing darkness of a pre-industrial night sky blazing with stars. And there, low in the west, just above where the sun had set an hour or two before, a point of light moving with quiet but unmistakable purpose. They watched it, they named it, they wrote it down, and somehow, incredibly, that record found its way to us. Across 5,000 years and countless upheavals of civilization, that small act of attention and documentation survived. That is what makes astronomy and the history of astronomy so moving to contemplate. It is one of the few human activities where the work of people who lived thousands of years ago is still directly relevant, still actively used, still connected in a living way to what scientists are doing today. Those Sumerian observers could not have imagined the spacecraft that would one day be sent to orbit Mercury, or the spectrometers that would analyze its surface composition, or the digital simulations that would model its volcanic history. But their observations, their clay tablets, their patient watching, all of it feeds into the same great accumulating river of human knowledge that eventually produced those spacecraft and those instruments. The ancient Greeks, too, had a rich and interesting relationship with Mercury, though they came to understand it in a somewhat roundabout way. For a long period of Greek history, Mercury was not recognized as a single object. It was instead believed to be two. When the bright, quick-moving point of light appeared in the pre-dawn sky, rising in the east just before the sun, visible for a short time in the pale gray light of early morning before being swallowed up in the sun's brilliance, the Greeks called it Apollo. Apollo, the god of light, of the sun, of dawning illumination. And when that same light appeared in the evening sky, showing up in the west just after sunset, glowing softly in the deepening twilight before disappearing below the horizon, they called it Hermes. Hermes the messenger, the traveler, the swift one. Two names, two identities, two entirely separate celestial objects, as far as the early Greeks were concerned. And you can understand why they thought that. Mercury never appears in both the morning and evening sky at the same time. When it is a morning object, it rises before the sun and is only visible in the east at dawn. When it is an evening object, it sets after the sun and is only visible in the west at dusk. There is no overlap. And because Mercury moves so quickly, because the geometry of its orbit around the sun produces this alternating appearance. Morning for a few weeks, then an interval of invisibility close to the sun, then evening for a few weeks, then another period of invisibility, it is genuinely understandable that observers without the benefit of modern orbital mechanics would assume they were seeing different things. It was the Pythagorean philosophers, or, in some accounts, a scholar named Parmenides of Elea, who first proposed that Apollo and Hermes were actually one and the same object. One planet, not two. The same wandering light, appearing sometimes before sunrise and sometimes after sunset, but always and only the same small, fast-moving world. It was a remarkable insight, and it led eventually to the consolidation of the two names into one, Hermes, which the Romans translated into their own mythology as Mercury. And Mercury it has remained, across 2,000 years of science and exploration, right up to the present day. Now, there is a quietly poignant detail in the history of Mercury's observation that I find myself returning to again and again, because it humanizes even the greatest of minds in such a gentle and unexpected way. Nicholas Copernicus, the Polish astronomer and mathematician who, in the early 16th century, published one of the most revolutionary ideas in the history of human thought. The idea that the Earth is not the center of the universe, that the Earth and all the other planets orbit the Sun. Nicholas Copernicus, despite his extraordinary achievements, despite his decades of painstaking astronomical work, reportedly never saw Mercury with his own eyes. Not once. He lived in the northern Polish lowlands, in a region crisscrossed by rivers and marshes and lakes. And in the early hours before sunrise, or in the lingering warmth of evening, the moisture rising from those bodies of water would gather near the horizon in a soft, persistent haze, a veil of mist, low and obstinate, sitting right at the level of the sky where Mercury could be found. Every time the planet was favorably placed for observation, every time it swung out to its greatest separation from the sun and hung there in the twilight, visible and bright, that mist was there to hide it. And so the man who gave us the heliocentric model of the solar system, the man who correctly described Mercury's place in the cosmic order and calculated its orbit with remarkable precision, never once saw the actual planet with his own eyes. He knew it was there. He was certain of it. His mathematical model predicted its movements accurately, and other astronomers confirmed it with their observations. But for Copernicus himself, Mercury remained always just out of reach, present in his equations, absent from his sky. There is something very tender about that. Something that reminds us that even the greatest scientists are also just people, subject to the same limitations and frustrations and small, quiet deprivations as the rest of us. After Copernicus, astronomy continued to develop. Telescopes were invented. Orbital calculations grew more and more precise. By the 19th century, astronomers had developed mathematical tools of extraordinary sophistication, grounded in the physics laid out by Isaac Newton in the 17th century. Newtonian gravity, the idea that every object with mass attracts every other object with mass, and that the strength of that attraction can be precisely calculated, had proven itself magnificently accurate. It had been used to predict the existence of Neptune before anyone ever saw it through a telescope, simply because astronomers noticed that Uranus wasn't quite moving the way it should, and worked out that another massive planet must be pulling on it. The prediction was made. A telescope was pointed in the right direction, and there was Neptune exactly where the math said it would be. Newtonian physics seemed unassailable, and yet Mercury wouldn't cooperate. Mercury's orbit had a strange quality to it. Its path around the sun was an ellipse, a slightly flattened circle, as Newton's laws predicted. But the ellipse itself wasn't fixed. It rotated. Slowly, over time, the point in Mercury's orbit where it passed closest to the sun, a point called the perihelion, moved. It shifted forward, gradually with each orbit, tracing out a slow rosette pattern rather than a fixed elliptical track. This phenomenon is called the precession of the perihelion, and a small amount of it was expected, due to the gravitational influences of the other planets on Mercury's orbit. But when astronomers calculated exactly how much precession those planetary influences should cause, and compared it to the precession they actually observed, there was a discrepancy. A small one, just 43 arcseconds per century, a tiny fraction of a degree, but a real one. A stubborn, persistent, repeatable discrepancy that Newtonian physics simply could not account for. The scientific community was troubled by this. Something was wrong, or something was missing, and the most popular solution proposed for many years was the idea that there must be another planet, a planet orbiting even closer to the sun than Mercury, whose gravitational pull was producing the extra precession. This hypothetical planet was named Vulcan, after the Roman god of fire and the forge. Vulcan felt like an appropriate name for something imagined to orbit so close to the blazing heat of the sun astronomers searched for it. During total solar eclipses, when the moon blocked the sun's light and the sky briefly darkened enough to reveal stars and other objects near the sun, astronomers would scan the region for any sign of a small, unknown planet. Reports trickled in from time to time. Someone claimed to have seen a dark dot crossing the sun's face, which they took to be Vulcan in transit. Papers were written. Excitement rippled through the astronomical community. And then the sightings couldn't be confirmed, and the excitement faded, and the search continued. Decades passed. The evidence for Vulcan never solidified. The sightings that had seemed promising turned out to be sunspots, or small known asteroids, or errors of observation. And gradually, reluctantly, the astronomical community began to accept that Vulcan probably did not exist. The inner solar system, it seemed, held no hidden world. And yet Mercury's orbit still wouldn't behave the way it should. The mystery remained unsolved. Until Albert Einstein. Einstein had been working for years on a new way of understanding gravity, not as a force acting between objects across empty space, as Newton had described it, but as a curvature of space-time itself, caused by the presence of mass and energy. In his vision, massive objects like the sun don't pull on planets with an invisible force. Rather, they bend the very fabric of space and time around them, and planets move along the natural curves of that bent fabric. It is a profoundly different picture of how the universe works. And in 1915, when Einstein completed the mathematical framework of what he called the general theory of relativity, one of the first things he did was apply his new equations to the orbit of Mercury. The result made him, by his own account, enormously excited. His equations predicted a precession of Mercury's perihelion of exactly 43 arcseconds per century. Exactly the discrepancy that had been puzzling astronomers for decades. Not approximately, not roughly, exactly. The number came out of the mathematics of general relativity as cleanly and precisely as if it had been put there on purpose. Mercury, the smallest planet in the solar system, the one named after the Roman messenger god because it moved so quickly across the sky, turned out to be the first real-world confirmation that Einstein's general theory of relativity correctly described the behavior of the universe. The phantom planet Vulcan was unnecessary. The mystery of the precessing orbit wasn't a sign that Newton's physics were incomplete in some minor, correctable way. It was a sign that an entirely new understanding of gravity, space, and time was needed, and Mercury's orbit had been quietly demonstrating that need for decades, waiting patiently for someone with the right framework to read what it was trying to say. It is hard to fully absorb how consequential that is. General relativity is not just a correction to Newtonian physics. It is the foundation of our modern understanding of the cosmos. It describes how black holes form and what happens at their boundaries. It predicts and explains the bending of light around massive objects, a phenomenon called gravitational lensing, now used by astronomers as a tool to study distant galaxies. It describes how the universe itself is structured and how it evolves over time. It is the framework within which scientists in 2015 detected gravitational waves, actual ripples in the fabric of space-time, produced by the collision of two black holes more than 1 billion light-years away. Every GPS satellite in orbit around the Earth must apply relativistic corrections to its timekeeping, because without those corrections, without accounting for the effects Einstein described, GPS systems would accumulate errors of several kilometers per day. The technology we rely on in our everyday lives, in our cars and our phones and our navigation systems, depends on the truth of general relativity. And it all traces one of its earliest confirmations back to a tiny, stubborn discrepancy in the orbit of a small, fast-moving planet that ancient Romans named after their swiftest god. And then there is one final idea to rest with tonight, one last quiet wonder to carry you towards sleep. From time to time, Mercury does something remarkable as seen from Earth. It crosses the face of the sun. Astronomers call this a transit. As Mercury travels along its orbit, which is tilted slightly relative to Earth's orbit, there are moments when the geometry lines up just right, when Mercury passes directly between the Earth and the Sun, moving across the bright solar disk from our point of view. On those occasions, observers on Earth with the proper equipment can watch Mercury as a tiny, perfectly circular black, smaller than any visible sunspot, creeping slowly across the vast glowing surface of our star. It is a humbling sight by all accounts. The Sun is enormous. Its diameter is more than 100 times that of the Earth, and Mercury, tiny Mercury, shows up against it as something barely perceptible. A dark speck, a period at the end of a very long sentence. And yet it moves with unmistakable purpose, tracing its slow arc across the solar disk over the course of several hours. A visible reminder that the solar system is a place of movement and precision and extraordinary, patient motion. Not every planet can produce a transit as seen from Earth. In fact, only 2 planets in our entire solar system are capable of it: Mercury and Venus. The reason is simple geometry. Only the planets that orbit closer to the Sun than we do, the ones that sometimes pass between us and the Sun, can be seen in transit from Earth. The outer planets, Mars, Jupiter, Saturn, Uranus, Neptune, they orbit farther out than we do, and so they can never position themselves between the Earth and the Sun. From an observer on those planets, it would be Earth that sometimes crosses the face of the Sun. But from our perspective, here on Earth, only Mercury and Venus can make that crossing. And Mercury does it about 13 times per century, which sounds frequent enough, but stretched across 100 years, it means roughly 1 transit per 8 years on average. And even that is not evenly distributed. Transits of Mercury tend to cluster around the months of May and November, because those are the times of year when Earth's position and Mercury's orbital geometry are most favorably aligned. The most recent transit of Mercury visible from Earth occurred in November of 2019. The next one will occur in 2032, and if you missed that one, the one after is in 2049. They are events worth watching for, rare enough to feel special, frequent enough to fall within a single human lifetime. A tiny dark circle making its slow, certain way across the face of our star, watched by people all over the world pointing their solar telescopes at the sky. Mercury has been making these crossings for billions of years, long before any human eye was there to witness them, long before the word transit existed or the word Mercury or the word planet. It has been moving, always in its swift and faithful orbit, carrying within it the secrets that would one day help us understand the very nature of space and time. And so we rest here gently at the end of this first long chapter of Mercury's story. We have traveled, tonight, from the clay tablets of the Sumerians to the mythology of ancient Greece. We have watched Mercury be mistaken for 2 planets, and then recognized as one. We have stood imaginatively at the top of a Sumerian ziggurat under a blazing pre-modern night sky, and we have shared, quietly, in the small frustration of Copernicus, peering toward the horizon through the mist and finding nothing. We have followed the trail of a phantom planet called Vulcan all the way to the equations of Einstein, and we have discovered that a tiny discrepancy in Mercury's orbit contained within it the seeds of the most consequential scientific theory of the 20th century. And we have watched, in imagination, a small black dot making its patient way across the burning face of the Sun. It is a long and layered story, and we have only just begun. The surface of Mercury waits to be described. Its craters and cliffs and vast ancient plains, its ice hidden in permanent shadow at the poles, the extraordinary length of its days and the strange way time moves there. All of that is still ahead. But not tonight. Tonight is for rest, for the slow, comfortable weight of sleep settling over you like something warm and familiar, for the breath growing slower and deeper, for the thoughts growing softer at the edges, less sharp, less insistent, drifting gradually toward the quiet country of dreams. Mercury is out there right now, somewhere in its orbit, racing around the sun at 47 kilometers per second, faster than any other planet, faithful to its ancient path, carrying its story patiently through the dark. And you are here, safe and still and resting. And that is exactly where you are meant to be. If the first thing Mercury's story asks us to do is look up, to cast our eyes toward the horizon at twilight and find that small, steady point of light racing along the edge of the sky, then the second thing it asks us to do is slow down, to sit quietly with numbers and distances and rhythms that, at first glance, seem almost too strange to be real. Because the way Mercury moves through space, the way it relates to the sun, the way it measures out its days and years, all of it is so different from anything we experience here on Earth that it requires a kind of patient, unhurried attention to really absorb. And patient and unhurried is exactly what we are tonight. So let your body settle a little more deeply into wherever you are resting right now. Let your shoulders drop. Let the muscles around your eyes soften. There is nothing here to figure out, nothing to solve, no test waiting at the end of this. There is only the quiet pleasure of learning, and the warmth of a voice in the dark, and the slow, comfortable drift toward sleep. We are in no hurry. We never were. Let us begin with the most fundamental fact about Mercury's place in the solar system, the one that shapes everything else about it, the one that is responsible for so many of the extraordinary qualities we are going to explore tonight. Mercury is the closest planet to the Sun. Of all the 8 planets in our solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, Mercury sits innermost. It occupies the first ring, the smallest orbit, the position nearest to that enormous, blazing, ancient star at the center of everything. All the other planets orbit farther out. All the other planets have Mercury between them and the Sun. It is, in that sense, the most solar of all the planets, the one most intimately acquainted with the star that powers our entire system. And yet, even for Mercury, that proximity is not constant, because Mercury's orbit is not a perfect circle. None of the planetary orbits are perfect circles. They are all ellipses, slightly stretched and flattened, with the Sun sitting not at the exact center but slightly off to one side. This is one of the foundational laws of planetary motion, first described by the German astronomer Johannes Kepler in the early 17th century. But while the ellipses of most planets are only very slightly elongated, close enough to circles that the difference is barely noticeable, Mercury's orbit is dramatically, unusually, noticeably stretched. It is the most eccentric orbit of any planet in the solar system. Eccentric in the astronomical sense, meaning not eccentric in personality or behavior, but eccentric in shape, elongated, oval, far from circular. And that eccentricity has real and measurable consequences for Mercury's distance from the Sun. At its closest point to the Sun, the point in its orbit called the perihelion, from the Greek words for near and sun, Mercury is approximately 46 million kilometers away from the Sun, 46 million kilometers. To us, living on a planet that sits about 150 million kilometers from the Sun on average, that sounds almost impossibly close. Less than a third of our own distance. Close enough that the Sun, seen from Mercury's surface at perihelion, would appear nearly 3 times larger in the sky than it does from Earth. A vast, overwhelming, luminous presence dominating the heavens in a way that we on Earth can barely imagine. But then Mercury continues along its orbit. It swings past perihelion and begins to move outward, following the long, looping curve of its ellipse away from the Sun. And by the time it reaches the farthest point of its orbit, the aphelion, from the Greek words for away from and sun, it is approximately 70 million kilometers from the Sun, 70 million kilometers, compared to 46 million at its closest. That is a difference of 24 million kilometers between Mercury's nearest and farthest points from the Sun, which means that during a single orbit, Mercury's distance from the Sun changes by more than 50%. It swings from intimate proximity to something considerably more distant, and then back again in the space of just 88 Earth days. Think about what that means in terms of the view from the surface. At perihelion, the Sun looms enormous in the sky, a blazing, overwhelming disk, nearly 3 times the angular size it appears from Earth. And then, as Mercury moves toward aphelion, the Sun gradually shrinks. Still huge by our standards, still an extraordinary dominant presence, but noticeably smaller than it was at the closest point. The difference between the apparent size of the Sun at perihelion and at aphelion, as seen from Mercury's surface, is genuinely striking. More dramatic than any seasonal change in the Sun's apparent size that we experience here on Earth. The Sun swells and shrinks with each Mercurian orbit in a way that would be deeply impressive to any hypothetical observer on the surface. Now, we have already touched on the speed at which Mercury moves through space, the quality that led the Romans to name it after their fastest god. But let us linger on that speed for a moment because it is truly remarkable. Mercury travels through space at an average speed of approximately 47 kilometers per second. 47 kilometers per second. Let us try to make that concrete. Kilometer is roughly 6/10 of a mile. So 47 kilometers per second is approximately 29 miles per second. In one single second, Mercury travels the distance of 29 miles. If you could somehow drive from New York City to Philadelphia, a journey of about 95 miles at Mercury's orbital speed, it would take you a little over 3 seconds. 3 seconds for a trip that takes a car driver around an hour and a half. Or think about it this way. Mercury's orbital speed is roughly 170,000 kilometers per hour. The fastest aircraft ever built by human beings, the legendary State Route 71 Blackbird, a reconnaissance aircraft developed in the 1960s, had a top speed of around 3,500 kilometers per hour. Mercury, in its orbit around the Sun, moves about 49 times faster than the fastest plane ever flown. And it maintains that speed continuously, relentlessly, every second of every day, year after year, century after century, for billions of years. The solar system's tireless sprinter, always racing, always moving, never resting. The consequence of all that speed is that Mercury's year, the time it takes to complete one full orbit around the Sun, is very short by our reckoning. Just 88 Earth days. 88 days. Not quite 3 of our months. By the time Earth has made it through winter and into the early weeks of spring, Mercury has already completed one full lap around the Sun and is well into its second. By the time Earth has made it around to summer, Mercury is on its 4th orbit. In the time it takes Earth to complete a single year, Mercury completes just over 4 of its own. 88 days. It is a strangely small number for something as significant as a year. A year is, in human experience, a substantial unit of time. It is long enough to contain seasons, to see a child grow noticeably older, to complete a major project, to travel somewhere distant and come home again changed. And yet on Mercury, a year slips by in less than 3 of our months. If you were somehow living on Mercury and aged at the rate of Mercurian years, you would celebrate your first birthday after just 88 Earth days. By the time an Earth-born person was celebrating their first birthday, a Mercury year person would already be turning 4. A 20-year-old Earth person would be the equivalent of 83 Mercury years old. Time, as always, is relative, not just in the Einsteinian sense we explored in our last segment, but in the simpler, more immediate sense of how long it takes a planet to go around its star. But here is where Mercury's story of time becomes truly strange. Truly, wonderfully, almost paradoxically strange. Because while Mercury completes its orbit around the Sun very quickly, 88 Earth days, it rotates on its own axis very slowly. Extraordinarily slowly, in fact, for a planet moving so fast through space. The time it takes for Mercury to complete one full rotation on its axis, what astronomers call a sidereal day, the rotation period measured against the background of distant stars, is approximately 59 Earth days. 59 Earth days for one rotation. At the equator of Mercury, the surface moves along with that rotation at a speed of only about 10 kilometers per hour. An averagely fit human being can cycle at around 20 or 25 kilometers per hour, which means that, in terms of its rotation, Mercury spins so slowly that a person on a bicycle could, in theory, keep pace with a point on Mercury's equator and have plenty of energy to spare. It is one of the slowest rotating planets in the solar system, despite being the fastest in terms of its orbit. Fast around the Sun, but turning on its own axis with glacial, meditative deliberateness. Now, when we talk about a day on Earth, we are almost always talking about what is called a solar day, the time from one sunrise to the next, or equivalently, from one moment when the Sun is at its highest point in the sky to the next. And a solar day on Earth is 24 hours. But a solar day is not the same as a sidereal day. A sidereal day is simply the time it takes a planet to rotate once relative to the distant stars. A solar day accounts for the fact that, while the planet is rotating, it is also moving along its orbit, so by the time it has completed one full rotation, it has also moved a little way around its orbit, and it needs to rotate just a tiny bit more before the Sun is back in the same position in the sky. On Earth, this difference is small. A solar day is only about 4 minutes longer than a sidereal day. But on Mercury, because the planet's orbital speed is so fast relative to its rotational speed, this difference becomes enormous. To figure out how long a solar day on Mercury lasts, how long from one sunrise to the next, you have to account for the fact that while Mercury is slowly rotating on its axis, it is also racing very quickly around the Sun. And those two motions interact in a way that produces a result that seems, at first encounter, almost unbelievable. A solar day on Mercury, one complete sunrise-to-sunrise cycle, lasts approximately 176 Earth days. 176 days, not quite 6 of our months. Mercury's day is twice as long as its year. Let that settle for a moment. By the time the Sun rises, crawls across the sky, sets, and then rises again in the same spot on Mercury, one complete Mercurian day has passed. Mercury has already completed 2 full orbits around the Sun. 2 years have passed in the time it took the Sun to move from one sunrise to the next. If you stood on Mercury's surface and watched patiently, with whatever sun protection and life support technology you might require, you would experience sunrise only once every 2 Mercurian years. The day is longer than the year. The Sun takes longer to travel across the sky than Mercury takes to go around it twice. This is a genuinely difficult thing to intuit, because our entire experience of time is built around the opposite assumption. For us, days are short and years are long. A day is something we get through quickly. A year feels like a substantial journey. On Mercury, those relationships are inverted in a way that feels almost like a riddle. The small cycle, the year, is contained within the large cycle, the day. A whole year fits neatly inside half a Mercurian day with room to spare. The reason for this peculiar arithmetic lies in a remarkable gravitational relationship between Mercury and the Sun called orbital resonance. Specifically, Mercury is locked in what astronomers call a 3:2 spin-orbit resonance with the Sun. What that means is this: for every 3 times Mercury rotates on its own axis, it completes exactly 2 orbits around the Sun. 3 rotations, 2 orbits. The ratio is precise, And it is not a coincidence. It is a consequence of the tidal forces that the Sun has been exerting on Mercury over billions of years. This kind of resonance is a gravitational lock, similar in principle to the tidal lock that keeps our own moon facing Earth with the same side always pointing toward us, though Mercury's resonance is of a different and slightly more complex type. The Sun's gravity, acting on the slight irregularities in Mercury's shape, gradually slowed and shaped Mercury's rotation over geological timescales until it settled into this stable 3:2 pattern. Mercury is not unique in being tidally influenced by its star, but its 3:2 resonance is more complex and more interesting than a simple 1:1 lock. And for a long time, astronomers actually believed Mercury was in a 1:1 lock, thought to be showing the same face to the Sun at all times, the way our moon shows the same face to Earth. It was only in 1965, when radar observations allowed scientists to actually measure Mercury's rotation rate directly, that the true 3:2 resonance was discovered. Before that, for decades, the textbooks were simply wrong. There is something I find quietly wonderful about that correction. Here was a planet that had been known and observed for thousands of years, that had been studied with telescopes for centuries, that bore a name ancient enough to predate the Roman Empire, and in 1965 scientists looked at it properly for the first time and discovered that a basic fact about it, the rate at which it spun, had been misunderstood all along. Mercury had been keeping that particular secret patient and uncomplaining, and it took the invention of radar astronomy to finally coax it out. Now, alongside its slow rotation and its eccentric orbit, there is one more quality of Mercury's orientation in space that shapes everything about its environment in a profound way. Mercury's axial tilt is almost exactly zero. On Earth, our axis is tilted at about 23.5 degrees relative to the plane of our orbit around the Sun. That tilt is the reason we have seasons. In summer, our hemisphere is tilted toward the Sun. The days are long, the Sun climbs high in the sky, and the warmth accumulates. In winter, our hemisphere is tilted away. The days are short, the Sun stays low, and the cold settles in. The entire seasonal rhythm of Earth, the thing that governs agriculture and migration and ecosystems and the cultural calendar of human civilization, exists because of that 23.5-degree tilt. Mercury's axial tilt is approximately 0.03 degrees. Not 3 degrees, 0.03 degrees, essentially zero. Mercury is almost perfectly upright in space, its rotational axis pointing almost exactly perpendicular to the plane of its orbit. And the consequence of that near-zero tilt is that Mercury has no seasons. None at all. The Sun rises and sets in very nearly the same path in Mercury's sky every single day, striking the surface from the same angles throughout the entire year. The North Pole of Mercury always experiences the same amount of sunlight as it does now. The South Pole, the equator, no summer, no winter, no spring, no autumn, just the same relentless, unchanging exposure, day after day, year after year, forever. For us, the seasonal cycle is so deeply woven into our experience of being alive on this planet that it is hard to imagine its absence. The shortening of the days in November, the bare branches of winter giving way to the first pale green of March, the long, golden evenings of July. Mercury knows none of this. Its sky has no memory of summer or winter, no anticipation of seasons turning. Just the same sun, blazing at the same angles, in a cycle that never varies. One of the most striking consequences of this zero tilt relates to Mercury's poles. Because Mercury is standing straight up with no axial lean, the Sun never rises very high above the horizon as seen from Mercury's polar regions. If you were standing at Mercury's North Pole, the Sun would perpetually skim along the horizon, never climbing high into the sky, never departing far below it, just hovering at that low angle indefinitely. The polar regions experience a kind of eternal twilight, with the sun always at that long, shallow, horizontal angle that we on Earth associate with the early minutes after sunrise or the last minutes before sunset. And one of the most extraordinary things about Mercury's polar regions, something we will explore in much more depth in a later segment, is that because the sun never climbs high enough to shine directly into certain deep craters near the poles, those craters exist in permanent shadow. They never receive direct sunlight. The floors of those craters have not been touched by the sun's light, perhaps, for billions of years. And in that permanent, deep, frigid shadow, something extraordinary has been found hiding. But we will come to that in its own time. For now, let us turn to what is perhaps the most visually spectacular consequence of Mercury's peculiar combination of slow rotation, fast orbit, and high orbital eccentricity. There is a phenomenon that can occur on Mercury's surface, a phenomenon that, if you were standing in the right place at the right time, you would witness with a combination of wonder and disbelief. It is called, informally, the double sunrise, or sometimes the retrograde sunrise, and it is one of the most surreal things that physics permits to happen on any world in our solar system. Here is how it works. Mercury's orbital speed is not constant. Because its orbit is so eccentric, so dramatically oval-shaped, Mercury moves faster when it is close to the Sun and slower when it is farther away. This is Kepler's second law of planetary motion, which states that a planet sweeps out equal areas of space in equal times, meaning it must speed up when it is near its star and slow down when it is far from it. For most planets, with their nearly circular orbits, this variation in speed is modest. But Mercury's highly eccentric orbit means that the difference between its fastest and slowest orbital speeds is quite large. At perihelion, closest approach to the Sun, Mercury is racing around its orbit exceptionally fast. So fast, in fact, that it is actually moving through space faster than it is rotating on its own axis. And this creates a situation where, for a brief period of time around perihelion, the Sun appears to move in a strange and counterintuitive way in Mercury's sky. An observer in the right location on Mercury's surface would watch the Sun rise above the eastern horizon, just as a sunrise on Earth begins. And then, as Mercury's orbital speed continues to exceed its rotational speed, the Sun would appear to stop its apparent motion across the sky, and then, impossibly dreamlike, begin to move backward. To set back below the eastern horizon it had only just risen above. The observer would watch the Sun retreat, sink back down, disappear, and then, as Mercury moves further along in its orbit and its speed decreases back toward normal, the rotation takes over again, and the Sun begins to rise once more from the east. Rising again, climbing, continuing on across the sky as if nothing unusual had happened. A second sunrise, in the same spot, from the same horizon, on the same morning. In other places on Mercury's surface, the same phenomenon plays out slightly differently. The Sun might be seen to slow, reverse course, trace a loop or a curve in the sky, and then resume its normal direction. And from locations near the poles, there are positions where a similar reversal can be witnessed at sunset rather than sunrise. The Sun appearing to set, rise briefly once more, and then finally set again for the long Mercurian night. There is no parallel to this on Earth. Our planet's orbit is circular enough, and its rotation fast enough relative to its orbital speed, that the Sun's path across our sky is a smooth, uninterrupted arc from east to west every single day without exception. We take that consistency for granted so completely that we have built language around it. Sunrise, sunset, the steady procession of daylight, without ever imagining that it might work differently on another world. On Mercury, For an observer in the right place at the right time, the sun reverses course. It rises, retreats, and rises again. It defies, for a short and astonishing interval, the pattern that every other planet in the solar system maintains without variation. Mercury does not follow the rules we are used to. It has its own rules, the rules of eccentricity and resonance and tidal locking and the competing rhythms of spin and orbit. And those rules produce a world where a day lasts longer than a year, where the sun can rise and set and rise again in the space of a single morning, where there are no seasons because the planet stands perfectly upright in space, where the poles are bathed in eternal, shallow twilight, and where craters on those polar floors have not seen sunlight in billions of years. It is a world of extremes in every direction, of paradoxes written in mathematics and expressed in the slow, majestic movements of a planet around its star. And yet, for all its strangeness, Mercury is governed by the same laws of physics that govern everything else in the universe. The same gravity that pulls your blanket over your shoulders, that keeps the atmosphere wrapped around our planet, that holds the moon in its orbit, that same gravity, acting over billions of years, shaped Mercury's orbit and spin and tilt into the extraordinary configuration it occupies today. There is nothing arbitrary about any of it. Every strange fact we have encountered tonight is the inevitable consequence of forces and processes playing out over timescales so vast they dwarf all of human history. And there is something deeply calming about that, if you let yourself feel it. The universe is not chaotic. It is not random. It is governed by precise, consistent, beautiful laws that operate the same way everywhere, from the smallest particle to the largest galaxy cluster. Mercury's double sunrise is not a glitch or an anomaly. It is physics doing exactly what physics does, working out its equations on a planetary scale, producing a result that is strange only by the limited standard of what we happen to experience from our particular vantage point on our particular planet. From a wider view, from the view of the universe itself, if such a thing could be imagined, Mercury's behavior is perfectly ordinary. It is simply what happens when you take a small, rocky planet, place it close to a massive star, let gravity shape its orbit into a pronounced ellipse, let the tidal forces of that star gradually slow and lock its rotation over billions of years, and then stand back and let the mathematics run. The result is a world where time works differently, where the sun behaves in ways we would find extraordinary, where the very meaning of a day or a year has to be rethought from the ground up. And now the numbers and the rhythms of Mercury's orbit have been laid gently before you. The 46 million kilometers of perihelion, the 70 million kilometers of aphelion, the 47 kilometers per second of orbital speed, the 88 Earth days of the Mercurian year, the 59 Earth days of the sidereal rotation, the 176 Earth days of the solar day, that long, slow cycle that contains 2 full years within its span. The 3:2 resonance, patient and precise, that locks 3 rotations to every 2 orbits like gears in a cosmic machine. The 0.03 degrees of axial tilt, so close to zero that seasons on Mercury are not merely mild but entirely absent. The polar twilight, the frozen craters, the double sunrise. Each one of these facts is a window into a world profoundly different from our own, and yet bound to us by the same physics, the same star, the same ancient solar system in which everything, every planet, every moon, every comet and asteroid and drifting grain of dust, was born together from the same vast cloud of gas and rock and ice more than 4.5 billion years ago. Mercury has been making its quick, eccentric orbit around the sun for all of that time. Billions of years of tight, fast loops around our star. Billions of years of slow rotation, of double sunrises, of polar shadows, of a day that outlasts a year. And it will continue for billions more, long after anything we could build or write or remember has faded. It is patient in the way that only planetary things can be patient, not because it chooses to be, but because it simply is. Because time at that scale is something different from what we mean when we use the word. So let Mercury's patience settle over you now. Let the thought of those billions of quiet orbits become something restful rather than overwhelming. Let the numbers that seemed large a little while ago, 46 million, 70 million, 176 days, 59 days, soften and lose their sharpness, become less like measurements and more like a kind of music. A slow, orbital music, playing in the dark, far from here, on a small and remarkable planet that has been faithfully circling our sun since long before there were eyes to watch it, or words to describe it, or a night like this one to drift quietly towards sleep within. The day is long, the year is short, the sun rises twice, and you are warm and still and resting. That is everything you need to know right now. There is a particular kind of wonder that comes not from enormity, but from smallness. We live in a culture that tends to celebrate the large, the tallest buildings, the widest rivers, the most massive stars. And there is, of course, genuine wonder to be found in scale, in the kind of bigness that makes you feel appropriately humble about your own place in the cosmos. But smallness has its own quiet magic. A seed that becomes a forest. A single cell that becomes a living creature. A planet that fits 18 times over inside its neighbor, and yet holds within its small frame some of the most remarkable physical properties in the entire solar system. Tonight, we are going to spend some time with Mercury's smallness, with what it means to be the least in one category and near the greatest in another, with what it feels like, in imagination, to arrive at a world that is modest in size but extraordinary in density, in history, and in the particular gravitational embrace it would offer to any visitor standing on its ancient, cratered surface. So let yourself arrive gently wherever you are right now. Let the weight of the day dissolve a little more with each breath. Your shoulders, your jaw, the space behind your eyes. Let all of it soften. There is no effort required here. No alertness, only the slow, easy drift of a mind following a story into the dark, and a body growing heavier and more comfortable with each passing minute. We are in no rush. Mercury has been waiting billions of years. Can wait a little longer while we settle in. Let us begin with the most immediately striking fact about Mercury when you compare it to the other worlds of our solar system. Mercury is the smallest planet. Of all 8 planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, Mercury is the smallest. It sits at the bottom of the size ranking, the most modest of the 8 in terms of sheer physical dimensions. Its diameter is approximately 4,880 kilometers. To put that in context, Earth's diameter is about 12,742 kilometers. Roughly 2.5 times larger than Mercury's. Jupiter, the largest planet in our solar system, has a diameter of about 142,000 kilometers, nearly 30 times larger than Mercury. If you placed Mercury next to Jupiter in a photograph, Mercury would look like a small marble sitting beside a basketball, a genuinely tiny thing in the company of a genuinely enormous one. But here is a comparison that perhaps captures Mercury's smallness more vividly than any other. Mercury is only slightly larger than Earth's own moon. Our moon, the familiar, beautiful, silver-white body that has governed human imagination, poetry, agriculture, and timekeeping for as long as human beings have existed, has a diameter of about 3,474 kilometers. Mercury's diameter, you will recall, is about 4,880 kilometers. So Mercury is larger than the Moon, yes, but not by as much as you might expect. If you were able to place them side by side in space, Mercury would be noticeably bigger, but the Moon would not look tiny in comparison. They are genuinely similar in scale. Similar enough that in photographs taken from great distances, the two bodies can look strikingly alike. Both gray, both heavily cratered, both ancient and geologically quiet, both bearing the scars of an early solar system that was far more violent and chaotic than the one we inhabit today. There is something that takes a moment to fully absorb about this comparison. The moon is something most of us have looked at all our lives. It is woven into our sense of the natural world. The thing that lights the night, that pulls the tides, that waxes and wanes through its monthly cycle with such reliable, comforting regularity that entire calendars were built around it. And Mercury, the planet, an actual planet orbiting the sun, a world in its own right with its own geology and history and physical character, is only a little bigger than that familiar companion. A little bigger than something we think of almost instinctively as small. And then there is a fact about Mercury's size that surprises almost everyone who hears it for the first time. 2 moons in our solar system, not planets but moons, satellites orbiting other planets, are actually larger than Mercury. Ganymede, which orbits Jupiter, and Titan, which orbits Saturn. Both of them exceed Mercury in diameter. Ganymede, the largest moon in the solar system, has a diameter of about 5,268 kilometers, making it not only larger than Mercury but also larger than the planet Pluto, and large enough that if it orbited the Sun directly rather than orbiting Jupiter, it would almost certainly be classified as a planet without any debate. Titan, Saturn's largest moon and the second largest moon in the solar system, has a diameter of about 5,149 kilometers, also larger than Mercury. So when we say Mercury is the smallest planet, it is worth appreciating just how small that actually is. It is smaller than 2 of the moons orbiting other planets. It is smaller than objects we classify as secondary, as satellites, as things that merely accompany the main players rather than being main players themselves. In the grand catalogue of significant round worlds in our solar system, Mercury barely edges its way into the top tier. It is a planet by virtue of its orbit and its relationship to the Sun, not by virtue of its size. And yet, and this is where Mercury's story becomes genuinely fascinating, where the smallness reveals itself as deceptive, size is far from the most important thing about Mercury's physical character. Because while Mercury may be the smallest planet, it is also the second densest planet in the entire solar system, second only to Earth itself. Density is a measure of how much mass is packed into a given volume. A bowling ball and a beach ball might be similar in size, but the bowling ball is far denser, far more mass concentrated into roughly the same amount of space. And Mercury, despite being small, is extraordinarily dense. Its average density is approximately 5.43 grams per cubic centimeter. For comparison, Earth's density is about 5.51 grams per cubic centimeter, just barely above Mercury's. Every other planet in the solar system is less dense than these two. Mars has a density of about 3.93 grams per cubic centimeter. Venus is about 5.24. Jupiter, despite its enormous mass, has an average density of only about 1.33 grams per cubic centimeter, slightly denser than water, because it is composed largely of hydrogen and helium gas rather than rock and metal. Saturn is even less dense than water. It would famously float if you could find an ocean large enough to hold it. But Mercury is dense, remarkably, almost anomalously dense for a planet its size. And the reason for that extraordinary density tells us something profound about Mercury's internal structure and its history. Most of Mercury's extraordinary density comes from its core. Mercury has an enormous iron core, enormous relative to its overall size. That is, scientists estimate that Mercury's core makes up somewhere between 55 and 85% of the planet's total radius, and accounts for roughly 60 to 70% of the planet's entire mass. The iron core of Mercury is, proportionally, the largest of any planet in the solar system. If you were to peel Mercury apart layer by layer, the thin crust, the mantle of silicate rock beneath it, and then the core, you would find that the core dominates the interior in a way that has no equivalent among the other planets. Earth has a large iron core too, but it accounts for a smaller fraction of Earth's total volume than Mercury's core accounts for of Mercury's. Why does Mercury have such a disproportionately large, dense, iron-rich core? That question has occupied planetary scientists for decades, and while a definitive answer remains somewhat elusive, the leading hypothesis involves the violent early history of the solar system. One widely accepted idea is that early in the solar system's history, Mercury was actually a larger planet, perhaps 2 or 3 times its current mass, but it was struck by one or more enormous impacts from other large bodies, collisions that stripped away much of its outer mantle of lighter rock and left behind a world that was disproportionately composed of its dense metal core. The lighter material was blasted away into space or accreted onto other bodies, and what remained was a small but extraordinarily dense world. Mostly iron, covered in a thin rocky shell, orbiting close to the Sun in the innermost position of the solar system. Another hypothesis suggests that the intense heat of the young Sun, when it was newly formed and extremely luminous, may have vaporized much of the lighter silicate material from Mercury's surface layers early in its history, leaving the denser iron-rich interior to dominate. Both mechanisms, giant impacts and solar evaporation, may have contributed to some degree, and the precise history of Mercury's interior remains one of the genuinely open questions of planetary science. But whatever the cause, the consequence is clear. Mercury is small and dense, a world that punches far above its weight in terms of mass per unit volume. A world whose internal structure is dominated by an iron heart that beats, metaphorically speaking, at the center of everything. A core so large, relative to the planet's size, that it has given Mercury something else remarkable. But we will come to Mercury's magnetic field in a later segment. For now, let us stay with the surface and with gravity. Surface gravity. The force that would pull you toward the ground if you were standing on another world. The thing that determines how heavy you feel, how high you can jump, how quickly objects fall when you drop them. On Earth, surface gravity is what we are used to, what we have calibrated our entire biology and our entire physical intuition against. We know what it feels like to lift something heavy, to feel our own weight pressing down through the soles of our feet, to experience the particular effort involved in climbing stairs or running uphill. All of that is Earth gravity. 1g, as scientists write it, the baseline against which everything else is measured. On Mercury, the surface gravity is approximately 38% of Earth's. Not 38 times 38%, 0.38 g, a little more than a third of what we experience here. And this lower gravity, despite Mercury's high density, is a direct consequence of its smaller size. There is simply less mass pulling you toward the center, and that reduced gravitational pull outweighs the effect of the higher density. What does 38% gravity actually feel like? It is an interesting thing to try to imagine. One way to approach it is through the simple arithmetic of weight. If you weigh 100 pounds here on Earth, or whatever your weight happens to be, the exact number is not important. What matters is the ratio. You would weigh only 38 pounds on Mercury. Not because your body has changed, not because any of your mass has gone anywhere, but because the planet pulling you toward its surface is smaller and less massive, and therefore pulls with less force. Your mass is the same. Your weight, the force with which gravity presses you against the ground, is reduced to a little more than a third of what you are used to. Think about what that would mean in practical terms, in the most everyday imaginable scenarios. A bag of groceries that feels heavy on Earth would feel remarkably light on Mercury. A piece of furniture that requires two people to lift on Earth could potentially be managed by one person on Mercury. Physical tasks that involve lifting and carrying would require dramatically less effort. And things that you drop would fall more slowly, not as slowly as they would on the Moon, where gravity is only about 16% of Earth's, but noticeably more slowly than they fall here. Objects would drift downward with a kind of measured deliberateness, taking longer to reach the ground than our instincts would predict. And jumping. If you can jump, say, half a meter off the ground here on Earth, a fairly modest jump, on Mercury you would be able to jump roughly 1 1/3 meters. More than 2.5 times as high. Not the extraordinary moon bounce that astronauts experienced on the lunar surface, where they could leap to extraordinary heights with relatively modest effort, but noticeably, entertainingly higher than anything possible here. Walking would feel effortless. Running would feel fleet and light. The entire physical experience of moving through space in your own body would be transformed by that lower gravitational pull. Now, there is a comparison worth making here that is both scientifically interesting and somewhat unexpected. Mercury's surface gravity, that 38% of Earth's, is almost identical to the surface gravity on Mars. Mars, which is a larger planet than Mercury, has a surface gravity of about 37 to 38% of Earth's. The two values are remarkably close, which means that an astronaut trained to move and work in Martian gravity would find Mercury's gravitational environment extremely familiar. The same light-footedness, the same adjusted sense of weight and effort, the same need to recalibrate throwing distances and the time it takes for falling objects to reach the ground. This similarity is something of a coincidence of mathematics. Mars is larger than Mercury but less dense, and these two factors balance out to produce nearly the same surface gravity. It is a good reminder that surface gravity is not simply a function of size or of density alone, but of both together, interacting in precise mathematical ways. You cannot look at a planet and simply guess its gravity from its apparent size. Mercury is small but dense. Mars is larger but less dense. And at the surface, they pull on you with nearly equal force. There is one more aspect of Mercury's physical character to touch on tonight. Two absences, actually, that are worth noting not just as simple facts but as things that shape the nature of the Mercurian world in important ways. Mercury has no moons, and Mercury has no ring system, no moons. In a solar system where many planets are accompanied by families of natural satellites, Earth has one, Mars has 2 small captured asteroids, Jupiter has at least 95 known moons, Saturn has well over 100 Mercury travels alone. It has no companion world orbiting it, no natural satellite of any kind. Just Mercury by itself in its tight orbit close to the Sun. There are a few reasons why this is not surprising when you think about it. Mercury is a small planet, and small planets have weaker gravity, which makes it harder for them to capture and retain moons. More significantly, Mercury orbits very close to the Sun, and the Sun's own powerful gravity complicates the dynamics considerably. Any moon in orbit around Mercury would need to be either very close to Mercury or very far from it. And in Mercury's case, neither option is easily stable for long periods. A moon orbiting close to Mercury would risk being disrupted by tidal forces. A moon orbiting far from Mercury would risk being pulled away by the Sun's dominant gravity. The region around Mercury where a stable satellite orbit is possible, what is called the Hill sphere, the region where a planet's gravity dominates over the Sun's, is quite small. Too small, it seems, to have retained any naturally captured moons through the billions of years of Mercury's history. And yet, The absence of moons gives Mercury a certain elemental simplicity. It is just the planet itself, unaccompanied, on its solitary journey around the sun. No satellites in tow. No orbital system to complicate its gravitational environment. Just Mercury, alone in its small, eccentric, fast-moving path, as it has been for billions of years. And then there are the rings, or rather, the absence of them. Mercury has no ring system, no icy particles circling it in flat, luminous bands the way Saturn does so spectacularly, or the way Uranus and Neptune have their own more modest ring systems. No rings at all. This is, again, not surprising for the same reasons that the absence of moons is not surprising. The same gravitational dynamics that make stable moons difficult around Mercury also make stable rings unlikely. And ring systems typically form either from the debris of a moon that has been broken apart by tidal forces, or from material that was never able to coalesce into a moon in the first place. With the gravitational environment around Mercury being as unstable as it is, neither mechanism produces anything lasting. But it is worth pausing on the absence of rings, even if only briefly, because rings are one of those features of planetary systems that seem, from a distance, purely decorative, purely aesthetic, a beautiful accident of orbital mechanics, but are actually deeply informative. The rings of Saturn tell us about the composition of the material orbiting there, about the gravitational interactions between the rings and Saturn's many moons, about the age and history of the ring system and the planet it surrounds. The presence of rings, or their absence, speaks to a planet's history, its gravitational environment, its relationship to its own satellites, and to the broader dynamics of the solar system. Mercury's ringless, moonless state is itself a kind of information, a quiet statement about the dominance of the Sun's gravity in the innermost solar system, and about the particular circumstances of Mercury's small but dense existence. So there it is, the planet in full physical profile as far as we have gone tonight, the smallest of the 8, similar in scale to our own moon, smaller, astonishingly, than 2 of the moons orbiting other planets in our solar system. A world you could fit 18 of inside the volume of Earth, and yet a world that is nearly as dense as Earth itself. A world with a colossal iron core, proportionally larger than any other planet's, buried beneath a thin rocky shell and pulling the whole structure toward that extraordinary second-place density ranking. A world whose surface gravity is just a little over a third of what we feel here, enough to let you jump higher and move with an unaccustomed lightness, but not so different as to feel entirely alien. A world that travels alone through space, with no moon for company and no rings to adorn it, just the planet itself on its solitary, faithful orbit around the sun. There is something very pure about that picture, if you let yourself sit with it. Something almost meditative about a world stripped down to its essentials. No satellites, no rings, no seasonal variation, no atmospheric weather systems to speak of. Just the planet, the core, the mantle, the ancient cratered surface, and the sun blazing overhead. Mercury is, in a sense, the most elemental of the terrestrial planets, the most reduced, the closest thing our solar system has to a simple statement of what a rocky world can be when you take away all the extras and leave only the fundamentals. And in that simplicity, in that smallness, in the quiet fact of a planet that travels alone and unpretentiously around our star, there is a kind of dignity. Mercury does not need to be large to be significant. It does not need moons or rings or seasons or a thick atmosphere to be worthy of our attention and our wonder. It has been there from nearly the beginning, in its tight orbit patiently circling, carrying within its dense iron heart a record of the early solar system that scientists are still working to fully decode. Small, dense, alone, and ancient, And somehow, because of all of that rather than in spite of it, endlessly fascinating. Let those qualities settle over you now. The smallness that is deceptive, the density that surprises, the gravity that would make you feel light on your feet, the simplicity of a world with no moons, no rings, no companions on its long journey around the sun. Let those images grow soft and comfortable at the edges, less like facts to be remembered and more like a landscape to drift through. A quiet, ancient, cratered landscape under a sky dominated by an enormous, blazing, close and magnificent sun. You are warm. You are still. The facts of Mercury's size and gravity are settled now, laid gently alongside everything else we have learned, building slowly into a picture of a world that rewards patience and attention and the willingness to be surprised by smallness. And there is more still to come: the surface, the craters, the extraordinary temperature swings, the ice and shadow, the thin and ghostly atmosphere. But all of that can wait for another segment, another drift into the dark. For now, Mercury is small and dense and alone in its orbit. And you are here, breathing slowly, growing heavier against whatever is holding you, letting the voice and the words and the quiet facts of a distant world carry you gently towards sleep. There is a particular kind of silence that most of us have never truly experienced. Not the silence of a quiet room or a peaceful forest or a still night in the countryside. Those silences are full in their own way of small sounds. The creak of a settling house, the distant call of an owl, the soft rhythm of wind moving through leaves. The silence I am thinking of is something different, something more complete, something that exists not merely as the absence of sound, but as the absence of the very medium through which sound travels. A silence so total and so fundamental that it is not really silence at all, in the way we normally use the word, but something closer to a physical condition of the universe itself. The silence of a world with no air. That is the silence of Mercury. Tonight we are going to step, in imagination, onto the surface of that airless world. We are going to look up at a sky unlike anything visible from Earth. We are going to feel, conceptually and gently, what it would mean to stand on a planet where the sky is always black and the sun is enormous and blazing and the ground beneath your feet is effectively a vacuum. We are going to explore what Mercury has instead of an atmosphere, and what that thin, ghostly, constantly shifting envelope of particles tells us about the relationship between this small planet and the star it orbits so closely. And we are going to do all of this slowly, without hurry, in the same unhurried way that Mercury itself exists, patient and ancient and indifferent to the passage of time. So settle in a little more. Let the weight of your body press comfortably into the surface beneath you. Let your breathing deepen, just a little without forcing it. Let it find its own natural rhythm, its own slow and easy tide. There is nothing to do right now but listen, nothing to hold on to, nothing to remember, just the words and the dark and the gradual, comfortable dissolution of the boundary between waking and sleep. Let us begin with the sky. If you were somehow standing on the surface of Mercury, protected, let us assume, by a sufficiently advanced spacesuit capable of handling everything the Mercurian environment would throw at you, and you looked upward, you would see something that our human intuition finds profoundly strange. The sky would be black, not the soft, deep blue of an Earth daytime sky, not the pale, washed-out blue of a hazy afternoon, not even the dark blue of the upper atmosphere seen from very high altitude. Black, the same dense, star-flecked black that we associate on Earth with the depths of the night, with the hours long after midnight when the sky reaches its darkest and most complete. But this blackness would not be the blackness of night. It would be the blackness of day, the full, blazing, unfiltered day of a world without air. On Earth, the reason our daytime sky is blue is because of our atmosphere. Sunlight entering the atmosphere is scattered by the molecules of nitrogen and oxygen that make up most of our air, and this scattering is selective shorter wavelengths of light, which correspond to the blue end of the visible spectrum, are scattered far more strongly than longer wavelengths. The result is that blue light is spread in all directions across the sky, reaching your eyes from every angle rather than just from the direction of the sun. This is called Rayleigh scattering, named after the 19th century British physicist Lord Rayleigh, who first described it mathematically. It is why sunsets are orange and red. When sunlight travels through more atmosphere near the horizon, the blue light is scattered away and only the longer, redder wavelengths reach your eyes directly. But all of that, every bit of that blue, every orange sunset, every pale gray overcast sky, requires an atmosphere, requires air, requires a substantial layer of gas between the surface and space, thick enough and dense enough to scatter light in meaningful quantities. Mercury, as we are about to explore in some depth, does not have that. And so there is nothing to scatter the sunlight, nothing to spread the blue across the dome of the sky, nothing to soften or diffuse the light in any way. The sun shines in the black sky of Mercury the way a lamp shines in a sealed, airless chamber, intensely, directly, casting razor-sharp shadows with no softening of edges, no atmospheric blur, no diffuse ambient light. You are either in brilliant, blazing sunlight or in absolute shadow. There is no middle ground, no gentle transition, just the hard boundary between light and dark, like the most extreme studio lighting imaginable, applied to an entire planet. The stars, too, would be visible from Mercury's surface during the day. Not faintly, not tentatively, the way you might occasionally catch a particularly bright star in an extremely clear Earth sky if you know exactly where to look. But properly, fully visible pinpoints of steady light against the black, right alongside the enormous blazing presence of the sun. Because there is no atmospheric scattering to wash them out, no blue glare to overwhelm their faint signals before they reach your eyes. Just the stars, steady and indifferent, visible in their true state regardless of whether the sun is in the sky or not. The daytime sky of Mercury would look, in most respects, like the nighttime sky of Earth, black, full of stars, except for one overwhelming difference: the sun. From the surface of Mercury, particularly at perihelion, at the closest point of Mercury's elliptical orbit, the sun does not look like the modest, familiar disk we see from Earth. It is enormous. It fills the sky in a way that is genuinely difficult to conceptualize from our vantage point. The apparent size of the sun, as seen from Mercury's surface at perihelion, is approximately 3 times larger than it appears from Earth. 3 times the angular diameter. If you hold your thumb up at arm's length on Earth, it is roughly wide enough to cover the sun's disk. From Mercury at perihelion, you would need something considerably wider than your thumb to block that disk. The sun would be a vast, overwhelming presence dominating the sky in a way that no astronomical body dominates ours. Not a manageable, comfortable distance away, as our sun seems from Earth but close. Imposingly, undeniably, almost oppressively close. And not just large, but extraordinarily bright. Sunlight at Mercury's distance from the sun, again, particularly at perihelion, is approximately 7 times more intense than the sunlight that reaches Earth's surface on a clear day. 7 times. The intensity of sunlight is already, on a clear summer day here, enough to damage your eyes and burn your skin in a matter of minutes without protection. On Mercury, that same solar radiation arrives with 7 times the intensity. Standing on Mercury's surface in direct sunlight without protection would not merely be uncomfortable or dangerous in the familiar way that sunburn is dangerous. It would be an entirely different category of experience. A bombardment of electromagnetic radiation that would be lethal without a suit specifically engineered to reflect and dissipate that extraordinary energy. And yet, paradoxically, and this is one of the most striking paradoxes in Mercury's entire story, despite all that solar intensity, despite the enormous blazing sun 3 times larger in the sky and 7 times brighter than it is from Earth, Mercury is not considered a habitable world. It does not sit in what astronomers call the habitable zone or the Goldilocks zone, the region around a star where conditions might be right for liquid water to exist on a planetary surface. And the reason for that is deeply connected to the very thing we are exploring tonight: the atmosphere, or rather, the lack of one. But before we get to habitability, let us properly understand what Mercury does have in the way of atmospheric covering. Because it is not absolutely nothing. There is something there, just not anything that deserves the word atmosphere in the usual sense. What Mercury has is called an exosphere. The distinction between an atmosphere and an exosphere is a meaningful one. An atmosphere, properly speaking, is a layer of gas dense enough that the molecules within it frequently collide with each other, creating pressure and enabling the kind of chemistry and heat trapping that we associate with planetary weather systems. Earth's atmosphere is an atmosphere in this full sense. So is Venus's and Mars's, and the thick gaseous envelopes surrounding the outer planets. An exosphere, by contrast, is a region where gas molecules are so sparse, so widely separated, that they rarely, if ever, collide with each other. Each molecule essentially travels independently, following its own ballistic trajectory, occasionally bouncing off the surface or escaping into space, without interacting in any meaningful way with its neighbors. An exosphere is less like a blanket of air and more like a thin, ephemeral mist of individual atoms, each going about its own business in effective isolation. Mercury's exosphere is of this tenuous, barely there variety. The pressure at Mercury's surface from this exosphere is somewhere around 1/quadrillionth of Earth's atmospheric pressure. 1/quadrillionth. That is a number so small it is almost beyond meaningful comparison. If you took all the air in a standard room, say a room about 5 meters by 5 meters by 3 meters, containing roughly 75 cubic meters of air, and distributed it equally over an area the size of Earth's entire surface, the resulting pressure would still be billions of times greater than the pressure Mercury's exosphere exerts. For almost any practical purpose, Mercury's surface is a vacuum. As complete and as empty a vacuum as anything we might deliberately create in a laboratory here on Earth. And yet, within that exosphere there are atoms. Sparse, lonely, widely separated atoms of several elements. The exosphere of Mercury has been found to contain hydrogen, helium, oxygen, sodium, calcium, and potassium. These are not gases that Mercury accumulated during its formation and retained over time, the way Earth retained its nitrogen and oxygen. Mercury is far too small and far too close to the Sun to have held on to primordial atmospheric gases. Any thick original atmosphere it might have had was stripped away long ago by the intense solar radiation and the solar wind. What exists today is something far more dynamic and impermanent. The hydrogen and helium in Mercury's exosphere come primarily from the solar wind. The solar wind is a continuous stream of charged particles, mostly protons and electrons, which are essentially the nuclei and electron shells of hydrogen and helium atoms, blowing outward from the sun in all directions at speeds of hundreds of kilometers per second. When these particles reach Mercury, some of them are captured temporarily by the planet's weak magnetic field and its surface, and they contribute to the exosphere. But they are also constantly being pushed away and lost, blasted off by the same solar wind that brought them, or given enough energy by solar radiation to escape Mercury's weak gravity entirely. The hydrogen and helium in Mercury's exosphere have an extremely short residence time. They are there today and gone tomorrow, replenished constantly by fresh arrivals from the sun. The sodium, calcium, and potassium in the exosphere have a different origin. These are elements that are actually present in Mercury's rocky surface, baked into the minerals and silicate compounds of the crust. They get into the exosphere through several processes. One is sputtering. When the solar wind particles strike the surface with enough energy, they knock surface atoms loose, sending them upward into the exosphere like billiard balls struck by a cue. Another is meteoroid impact vaporization. When small meteoroids and dust particles strike Mercury's surface, the energy of the impact is enough to vaporize surface material and send atoms flying upward. And a third mechanism is simply the intense heat of the Mercurian surface, which can, in some regions, be enough to thermally excite surface atoms and allow them to escape as vapor. So Mercury's exosphere is a kind of constantly renewing stream of material atoms being fed into it from below, from the surface, and from outside, from the solar wind, while simultaneously being stripped away by radiation pressure and the solar wind at the top. It is a dynamic, perpetually cycling system that happens to look, from the outside, like something very close to nothing at all. An extremely thin, constantly refreshed veil of lonely atoms between the surface and space. And within this thin veil, there is something extraordinary. Something that, when astronomers discovered it, turned a few heads and provoked genuine wonder. Mercury has a tail. Not a tail in the way that comets have tails. Mercury is not losing material at the dramatic rate that a comet does when it passes close to the sun. But Mercury does have a structure extending away from the sun on the side facing away from it. A long, faint stream of sodium atoms pushed away from the planet by the pressure of sunlight itself. Radiation pressure, the actual physical force exerted by photons of light, is enough to push these lightweight sodium atoms away from Mercury and downstream, in the antisolar direction, creating a comet-like tail that has been detected and imaged by ground-based telescopes using special filters tuned to the specific wavelength of light emitted by sodium. Mercury's sodium tail can extend for millions of kilometers behind the planet, pushed by the ceaseless pressure of sunlight. It is not visible to the naked eye, and it requires specialized equipment to detect. But it is real, and it is there, and it is a remarkable testament to the strange environment Mercury inhabits. Close enough to the sun that the pressure of sunlight itself is sufficient to strip atoms from the planet's exosphere and blow them across millions of kilometers of space in a luminous, ghostly stream. A comet-like tail on a planet. Sodium atoms, blown from the surface of the innermost planet by photons of light, trailing behind Mercury in the dark. Now, let us return to the question of habitability. Because the absence of a real atmosphere is not merely an interesting physical detail about Mercury. It is the central reason why Mercury, despite being in some ways so close to the sun's energy source, is not considered a world where life as we know it could exist. And the logic of why that is the case leads us to one of the most important concepts in the search for life beyond Earth: the concept of the habitable zone. The habitable zone, sometimes called the Goldilocks zone after the fairy tale character who wanted things not too hot and not too cold but just right, is defined as the range of distances from a star within which a planet with a sufficient atmosphere could maintain liquid water on its surface. The key phrase there is "with a sufficient atmosphere," because the habitable zone is not simply about distance from the star. It is about the combination of distance and atmospheric conditions. An atmosphere acts as a regulating layer. It traps some of the star's heat through the greenhouse effect, keeping the surface warmer than it would otherwise be, and it moderates temperature swings by distributing heat around the planet and acting as a thermal buffer. Without an atmosphere, the surface of a planet swings between extremes, blazing hot in sunlight, bitterly cold in shadow, with nothing to modulate those swings or maintain a stable, moderate temperature at which liquid water could persist. Mercury sits inside the inner edge of the Sun's habitable zone. It is, by current distance alone, too close to the Sun for liquid water to exist on its surface even with a substantial atmosphere. But the absence of any meaningful atmosphere makes things dramatically more extreme. Without any greenhouse effect, without any atmospheric heat distribution, without any mechanism to smooth out the temperature difference between the sunlit and shadowed hemispheres, Mercury's surface temperatures range from some of the hottest to some of the coldest in the solar system. We will explore those temperature extremes in detail in a later segment. But the point, for now, is that an atmosphere is not merely a convenience or a source of air to breathe. It is a fundamental component of the conditions necessary for a planet to maintain the kind of stable, moderate environment in which life might arise and sustain itself. Mercury has no such component. The surface is a vacuum. Its temperature swings are violent and unmediated. Its relationship to the Sun is one of raw, unfiltered exposure, no buffer, no moderator, no protective layer between the surface and everything the Sun can throw at it. In that sense, Mercury is about as inhospitable as a world can be, while still being a solid, rocky place rather than a gas giant or a radiation-blasted neutron star. And this brings us to one final thought for tonight: the idea of terraforming. Terraforming is the speculative concept of deliberately modifying a planet's environment to make it suitable for human habitation. It is a concept that has been seriously discussed in scientific and engineering terms for planets like Mars, which has some qualities: a solid surface, a thin existing atmosphere, evidence of past water, that make it at least conceivable as a target for future terraforming efforts. The challenges are enormous, and the technology to accomplish anything even approaching terraforming Mars does not currently exist and may not for centuries. But the conversation is not entirely in the realm of pure science fiction. Mars has features that make the goal at least imaginable in principle. Mercury does not. Terraforming Mercury is considered, by virtually everyone who has thought carefully about it, to be beyond the reach of any plausible technology. Not merely because of the engineering challenges involved in giving it an atmosphere, though those are formidable, but because of the fundamental problem of its location. Mercury is simply too close to the Sun. Any atmosphere you attempted to give it would be subjected to the same solar radiation and solar wind that stripped away whatever atmosphere Mercury originally had. The solar pressure at Mercury's distance is powerful enough to push sodium atoms across millions of kilometers of space. An artificially created atmosphere, composed of heavier molecules than sodium, yes, but still, would be subjected to relentless stripping by solar radiation and the solar wind. Maintaining it would require a constant, massive replenishment effort that goes far beyond anything we could imagine as a practical undertaking. Furthermore, the temperature extremes on Mercury's surface, swinging from high enough to melt lead on the sunlit side to hundreds of degrees below zero in permanent shadow, are a consequence not just of the lack of atmosphere but of Mercury's proximity to the Sun and its slow rotation. Even with an atmosphere, Managing those extremes at Mercury's distance from the Sun would require engineering solutions that strain even optimistic visions of future technology. And so Mercury remains, for the foreseeable future of any realistic human planning, a world to be visited and studied rather than inhabited. A world to send spacecraft to, and we have sent spacecraft there and discovered extraordinary things as we will explore in later segments, but not a world to live on. Not a world to breathe on, or to stand unprotected on, or to look up from at a blue sky. Because there is no blue sky. There is only the black and the stars and the sun, enormous and blazing and close, shining down with 7 times the intensity we receive on Earth onto a surface as bare and exposed and unprotected as any in the solar system. And yet, even in that starkness, there is beauty. There is the beauty of a sky that is always night while the sun blazes overhead. The beauty of stars visible in full daylight, steady and unblinking in the airless black. The beauty of that sodium tail, ghostly and luminous, streaming away from the planet in the anti-solar direction like the trail of a runner who has already passed by. The beauty of a world so thoroughly honestly itself, so completely without pretension or decoration, so entirely reduced to its own essential nature, that looking at it clearly requires you to let go of all your assumptions about what a planet is supposed to look like. Mercury does not look like what we expect. It does not behave like what we expect. It does not offer the comforts of atmosphere or weather or moderate temperature. It offers instead something rarer and in its own way more valuable. A completely unfiltered view of what a rocky world looks like when stripped of every moderating influence, sitting in the raw, unmediated presence of a star. A world that is, in the truest sense, naked before the sun. Let that image settle gently into your mind. The black sky, the blazing, enormous Sunday, the sharp-edged shadows, the silent, airless surface, the ghost of sodium atoms trailing behind the planet in a luminous stream. The absolute, total, fundamental quiet of a world with nothing between it and space. And here you are, insulated and warm, with the comfortable weight of blankets and the soft presence of air all around you. Air that you have never needed to think about, air that has always simply been there, moderating and buffering and softening the world for you in 10,000 ways you have never had occasion to notice. Feel it now if you like. The simple, extraordinary fact of being surrounded by air, by an atmosphere that scatters sunlight into blue and orange and gold, that keeps the temperature within the range your body was built for, that carries sound from one place to another so that voices can travel and music can exist and the world has texture and depth beyond what the eyes alone can provide. Mercury has none of that, and perhaps knowing that makes the air around you feel, just for a moment, like the remarkable gift it actually is. You are warm and breathing and still. Mercury is airless, ancient, and alone in its orbit. Both of these things are true simultaneously right now in the same universe, and somehow that is a deeply comfortable thought to carry into sleep. The contrast between the vast, bare, silent world of Mercury and the small, warm, breathing moment you are living in. There is nowhere you need to be, nothing you need to do, only the slow, deepening comfort of rest and the quiet knowledge that the universe, in all its strangeness and scale and beauty, is doing exactly what it has always done. Rest now. The sky is black over Mercury and full of stars. And here, wherever you are, it is exactly as it should be. There is an old idea, found in one form or another across many of the world's cultures and mythologies, that the universe is built from opposites. Light and dark, order and chaos, the heat of summer and the cold of winter. The ancient Greeks spoke of opposing forces held in tension as the foundation of all natural things. The Chinese philosophical tradition described the universe in terms of yin and yang, complementary, interdependent polarities that together define the whole. Many indigenous traditions around the world describe creation itself as the product of contrasting forces coming into relationship with each other. And while modern science does not speak in quite those terms, there is something in that ancient intuition that resonates when you consider what we know about Mercury. Because Mercury is, in the most literal and measurable physical sense, a planet of extremes. A world where the contrast between opposites is pushed further than anywhere else in the solar system. A world that is simultaneously, depending on where you are standing on its surface, one of the hottest places and one of the coldest places among all the solid worlds that orbit our sun. A world of fire and ice, existing not in metaphor but in geological fact, separated in some cases by only a few kilometers of ancient, cratered terrain. Let the idea of that contrast settle softly into your mind as your body settles into rest. The fire and the ice, the two extremes, coexisting on the same small planet, under the same enormous blazing Sunday. We are going to spend this segment exploring both ends of that spectrum, the astonishing heat of Mercury's sunlit surface, the astonishing cold of its shadowed depths, and the extraordinary fact that connects them in a way that planetary scientists did not expect and that still, when you stop to think about it carefully, seems almost too strange to be true. So breathe slowly. Let your thoughts grow quieter. Let the events of the day, whatever they were, recede a little further into the background. There is only this now, the warmth of wherever you are lying, the sound of a voice in the dark, and the story of a planet that holds the solar system's most dramatic temperature range within its small and ancient frame. Let us begin with the heat. Mercury's daytime surface temperature can reach approximately 430 degrees Celsius. In Fahrenheit, that is around 800 degrees. Let us try to make that number real, because 430 degrees Celsius is the kind of figure that is easy to hear and difficult to truly feel the significance of. Consider that water boils at 100 degrees Celsius at sea level. Mercury's daytime surface temperature is more than 4 times the boiling point of water. Consider that the temperature at which you might bake bread in an oven is somewhere around 200 degrees Celsius. Mercury's daytime surface is more than twice that hot. Consider that lead, the heavy, dense metal, melts at approximately 327 degrees Celsius. On Mercury's sunlit surface, lead would be a liquid. It would flow. It would puddle in the hollows of the ancient craters and creep slowly down the slopes of the great volcanic plains. Not hypothetically or under special laboratory conditions, but simply because the ambient temperature of the surface in full sunlight exceeds the melting point of lead. Zinc melts at 420 degrees Celsius, close to Mercury's maximum surface temperature. Tin melts at 232 degrees Celsius and would be thoroughly liquid on the sunlit surface. Even some aluminum alloys begin to soften and lose structural integrity at temperatures approaching those found on Mercury's dayside. These are not exotic, laboratory-specific materials. These are metals that human beings have been smelting and shaping for thousands of years, metals that we use in everyday objects all around us. And on Mercury's sunlit surface, they would melt. They would simply, straightforwardly, quietly melt. The reason for this extreme heat is, at this point in our journey through Mercury's story, not difficult to understand. We have already talked about how close Mercury is to the Sun, as close as 46 million kilometers at perihelion, bathed in sunlight 7 times more intense than what reaches Earth's surface. We have talked about how Mercury's surface is effectively a vacuum, with no atmosphere to moderate or distribute that solar energy. And we have talked about Mercury's extraordinary slow rotation, the fact that a single point on Mercury's equator can be exposed to direct sunlight for the equivalent of many Earth weeks before the slow rotation of the planet finally carries it around into darkness. All of those factors together, the proximity to the Sun, the absence of atmospheric buffering, and the extended duration of solar exposure during the long Mercurian day, combine to drive the surface temperature up to those extraordinary heights. And then the night comes. On Earth, the temperature drop between daytime and nighttime is real and noticeable. sometimes dramatically so in desert environments, where the absence of moisture in the air means less heat is retained after sunset. But even in the most extreme terrestrial desert nights, temperatures rarely fall below -20 or -30 degrees Celsius. The atmosphere, even a dry and thin one, still retains enough heat to prevent truly extreme cold from setting in. And of course, on much of Earth, the oceans and the atmosphere work together to distribute heat globally and moderate temperature swings on a planetary scale. Mercury has none of these moderating systems. When the slow Mercurian rotation finally carries a point on the surface out of sunlight and into the long, dark night, there is nothing to retain the heat that the sun has been pouring into that surface for weeks. No atmosphere to trap infrared radiation and radiate it slowly back. No ocean to release stored warmth. No weather system to carry heat from warmer regions to colder ones. The heat simply escapes, radiates directly away into space from the surface rocks with nothing to slow it down or catch it. And the temperature plummets, rapidly and completely, falling toward the baseline of a surface exposed to the cold of space with no insulation whatsoever. Mercury's nighttime surface temperature falls to approximately -180 degrees Celsius. In Fahrenheit, that is around -290. -180 degrees Celsius is cold enough to freeze carbon dioxide, which solidifies at -78 degrees Celsius several times over. It is cold enough that oxygen, which we breathe as a gas at room temperature, would begin to approach its liquid state. Oxygen liquefies at -183 degrees Celsius. It is cold enough that nitrogen, the most abundant component of Earth's atmosphere, would be very close to liquefying as well. Nitrogen liquefies at -196 degrees Celsius. The nighttime surface of Mercury is, in essence, cold enough to turn the gases of our own atmosphere into liquids or solids. A world where the air we breathe would freeze and fall as snow, if only there were any air there to freeze. The temperature swing between Mercury's daytime maximum and nighttime minimum is therefore approximately 610 degrees Celsius. 610 degrees of difference between the hottest and the coldest temperatures experienced on the surface of the same planet. That is the largest temperature range of any planet in our solar system. Not the largest compared to some planets, the largest of all of them. Mercury holds that particular record firmly and by a significant margin. No other planet experiences such a dramatic swing between its warmest and coldest surface temperatures. And now comes the fact that surprises almost everyone who encounters it for the first time. The fact that, despite all of this, despite the enormous blazing sun 3 times larger in the sky than it appears from Earth, despite the 7 times greater solar intensity, despite the daytime temperatures that melt lead and could melt zinc, despite holding the record for the greatest temperature range in the solar system, Mercury is not the hottest planet. Not even close to the hottest planet. That distinction belongs to Venus. Venus, which orbits farther from the Sun than Mercury, comfortably outside Mercury's orbit, receiving substantially less solar energy per square meter of its surface, maintains an average surface temperature of approximately 465 degrees Celsius. Constantly, at all latitudes on the day side and the night side alike, at the poles and at the equator, at the surface and just above it. Venus is hotter on average than Mercury's maximum daytime temperature. The hottest Mercury ever gets, in the most sunlit spot at perihelion, is still cooler than the average temperature on Venus on any given day in any given location. How is that possible? How can a planet farther from the Sun be hotter than the planet closest to the Sun? The answer, of course, is atmosphere. Venus has one of the most extreme atmospheres in the solar system, a thick, dense, crushing blanket of carbon dioxide roughly 90 times the pressure of Earth's atmosphere at the surface, laced with clouds of sulfuric acid and trapping heat with an efficiency that makes Earth's own greenhouse effect look modest by comparison. The greenhouse effect on Venus is so powerful, so complete, so effective at trapping every bit of heat that the sun delivers and preventing any of it from escaping back into space, that the surface temperature is maintained at that extraordinary 465 degrees Celsius essentially everywhere, at all times regardless of sunlight. The night side of Venus is almost exactly as hot as the day side. The poles are almost exactly as hot as the equator. The atmosphere distributes and retains heat with such overwhelming thoroughness that the planet has, in effect, one temperature. Mercury, by contrast, has no atmosphere to create a greenhouse effect, no mechanism to retain heat, no way to smooth out the temperature difference between sunlit and shadowed regions. And so while Mercury can spike to extraordinary temperatures in direct sunlight, it cannot maintain those temperatures the way Venus does. The heat comes and goes with the slow turning of the planet, burning in the day, plunging in the night. Venus broods at a constant atmosphere-maintained heat that Mercury, for all its solar proximity, simply cannot sustain. This comparison between Mercury and Venus is, in miniature, one of the most important lessons in planetary science. It is a demonstration of the overwhelming importance of atmosphere in determining a planet's thermal character. Distance from the star matters. Solar intensity matters. But the presence or absence of an atmosphere, and the composition and thickness of that atmosphere, can override both of those factors. Venus wins the competition for hottest planet not because it is closest to the Sun, but because it has the most effective heat-trapping system. Mercury loses that competition not because it is too close, but because it has nothing to trap heat with at all. The lesson is as clear as it is profound. The atmosphere is not merely the air we breathe. It is the thermostat of the world. And now, with all of that established, with the extremes of Mercury's temperature range fully laid out, with the fire of its days and the cold of its nights made as vivid as words can make them, with the counterintuitive lesson of Venus and the greenhouse effect absorbed, we arrive at what is perhaps the most astonishing single fact in Mercury's entire story. A fact that, when scientists first seriously considered it, seemed almost absurd on its face. A fact that required extraordinary evidence to be believed, and that still, even now that the evidence is abundant and unambiguous, carries with it a quality of the improbable and the wonderful. There is ice on Mercury, water ice, frozen water, the same substance that fills our oceans and falls as snow and forms the glaciers and ice caps of our own world. Billions of tons of it, sitting on the surface of the planet closest to the Sun, the planet where daytime temperatures melt lead, the planet with the most extreme temperature range in the solar system. Water ice, hidden and patient and ancient on Mercury. The story of how we came to know this is itself worth telling slowly, because it illustrates one of the most elegant and satisfying sequences in the history of planetary science. The sequence from theoretical prediction to observational confirmation to full scientific acceptance. The idea that ice might exist on Mercury was first suggested, tentatively and speculatively, based on a simple piece of geometric reasoning. We know, as we have discussed, that Mercury has virtually no axial tilt. Its axis of rotation is nearly perfectly perpendicular to the plane of its orbit. And we know that Mercury's surface topography, like that of the Moon, includes numerous deep impact craters, some of them quite large and deep, with steep walls that cast long shadows across their floors. At the poles of Mercury, where the sun never rises more than a fraction of a degree above the horizon, the geometry of those deep craters means that their floors are in permanent shadow. The sun's rays, skimming along so close to the horizon, simply cannot reach into the depths of those craters. The floors are never illuminated. They have not been in direct sunlight for perhaps billions of years. And in permanent shadow, on a world with no atmosphere to distribute heat, a very interesting thing happens. The temperature does not follow Mercury's dramatic swings between 430 and -180 degrees. It simply stays cold. perpetually, consistently, profoundly cold. Scientists calculated that the floors of these permanently shadowed polar craters could maintain temperatures as low as -170 to -200 degrees Celsius, temperatures at which water ice would be stable for geologically enormous timescales. Once ice got in there, however it arrived, it would stay. Nothing would melt it. Nothing would sublimate it away. The shadow is too deep and too permanent, and the temperature too consistently cold for the ice to go anywhere. It would simply remain year after year, orbit after orbit, century after century, millennium after millennium. So the theoretical case for ice on Mercury was made. It was a clean and logical prediction. These craters exist, they are in permanent shadow, the temperatures there are below the stability threshold for water ice. Therefore, if any water ever reached those locations, it would still be there. But knowing that ice could theoretically be stable is not the same as knowing it is actually there. The prediction needed to be tested. The first strong evidence came from radar astronomy. In 1991, scientists used the Arecibo radio telescope in Puerto Rico, at the time the largest single-dish radio telescope in the world, to bounce radar signals off Mercury's surface. Radar astronomy works by sending out a pulse of radio waves and analyzing what comes back. Different surface materials reflect radar differently. Rocky surfaces have one characteristic radar signature, rough terrain has another, and ice, as it happens, is highly reflective to radar in a very distinctive way. When radar waves strike a large body of water ice, they tend to bounce back with unusually high reflectivity and with a particular pattern of polarization, a specific orientation of the reflected waves, that is quite different from the radar signature of bare rock. When the Arecibo radar results came back from Mercury, there were bright, highly reflective spots at the poles. Extremely bright, distinctively bright in exactly the way that ice is bright to radar. The locations of those bright spots corresponded almost perfectly to the predicted positions of permanently shadowed craters near Mercury's north and south poles. The radar was, in essence, bouncing back from something that looked exactly like ice, in exactly the places where ice was predicted to be, on a planet where virtually no one had previously thought to look for it. The scientific community was cautious. Ice on Mercury seemed so counterintuitive, so paradoxical given the planet's reputation as a scorching, sun-blasted wasteland, that alternative explanations were considered. Could the radar brightness be caused by something other than ice? Sulfur has some similar radar properties. Certain silicate minerals can also be somewhat reflective to radar. The debate continued for years, with different researchers weighing the evidence and considering the alternatives. But the case for ice strengthened over time. As our understanding of Mercury improved, as additional observations were made, and as spacecraft began visiting the planet, the evidence accumulated. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, and which we will spend a great deal of time discussing in a later segment, carried instruments that provided additional measurements of the polar regions. It found that the radar-bright deposits were located specifically in regions that thermal models predicted would be in permanent shadow. The correspondence was precise. It found surface material in those regions that was consistent with water ice mixed with dark organic material. It measured neutron fluxes from the polar regions that were consistent with the presence of hydrogen, the hydrogen in water molecules, at or near the surface. By the time all of that evidence was assembled and analyzed, the scientific consensus was firm. There is water ice on Mercury. There are billions of tons of it. Some estimates suggest the total volume of ice in Mercury's polar deposits could be comparable to the volume of ice in some of Earth's largest glaciers. Vast quantities, by any ordinary measure, of frozen water sitting in the cold darkness of permanently shadowed craters on the planet closest to the Sun. The ice is thought to have arrived on Mercury through the same mechanism that brought ice to the Moon and potentially to other inner solar system bodies. the impacts of comets and water-rich asteroids over billions of years. Comets are essentially large balls of ice and dust. When a comet strikes a planet, the impact vaporizes most of the material, sending it in all directions. But some fraction of the water vapor produced by the impact will drift to the poles, reach a permanently shadowed region, and freeze. Over billions of years and billions of impacts, those small contributions accumulate. Layer by layer, delivery by delivery, the ice builds up in the cold, dark, permanent shadow of ancient craters until there are billions of tons of it sitting quietly in the dark, undisturbed and unremarkable, waiting for a civilization with radar telescopes to find it. There is something deeply poetic about that image. The ice on Mercury is not recent. It is not the product of some unusual recent event. It has been there, most likely, for hundreds of millions or billions of years. Ancient ice, accumulated through patient cosmic delivery over geological timescales, preserved by nothing more than the geometry of a slightly tilted crater wall and the fact that the sun on Mercury never climbs high enough above the horizon to shine into those deep, cold, shadowed floors. It is some of the oldest, most patiently preserved water in the inner solar system, a record of the cometary bombardment of the early solar system, frozen in time and in shadow, on a world where the surface nearby would melt lead. Fire and ice. 430 degrees and minus 180 degrees. Lead that flows like water in the full sun, and ancient ice preserved for billions of years in the shadow of a crater wall. Both of these extremes exist on the same small world, at the same moment right now. While the sunlit surface of Mercury bakes at temperatures that would be lethal to any known form of life in an instant, a few kilometers away, not even that far, in some cases water ice sits in the dark and the cold, unchanged and unchanging, exactly as it has been for longer than any human institution, any civilization, any species recognizable as human has existed. The universe contains multitudes. It holds contradictions not as errors to be resolved, but as features to be marveled at. Mercury is not confused about being both the hottest and the most ice-preserved world in terms of polar deposits in the inner solar system. It is simply following the laws of physics with complete fidelity, the same laws that make sunlight hot and shadows cold, that make lead melt and water freeze, that make radar waves bounce brightly off ice in a way that can be detected from hundreds of millions of kilometers away by a radio telescope in Puerto Rico pointed at the sky. Everything we have talked about tonight follows inevitably from those laws. The daytime heat follows from proximity to the sun and the absence of atmosphere. The nighttime cold follows from the absence of any mechanism to retain heat. The superiority of Venus's temperature follows from the overwhelming power of a thick greenhouse atmosphere. And the ice follows from the combination of zero axial tilt, deep craters, permanent shadow, and billions of years of patient accumulation. None of it is accidental. All of it is physics doing what physics always does, producing, from a small set of consistent and universal principles, an endless variety of outcomes that seem strange and surprising only because our window of experience is so narrow. Let the fire and the ice of Mercury become, in your imagination, not two separate facts but one unified picture. A small planet, striped in extremes, blazing where the sun reaches, frozen where it cannot. A world that holds both the scorching and the frigid within its ancient frame, not in contradiction but in perfect physical consistency. A world that is, in this as in so many other ways, simply the most extreme version of principles that operate everywhere. And as that picture settles and softens in your mind, let the temperature of wherever you are become something you notice and appreciate. The warmth of a bed or a blanket, or a room heated to a temperature your body finds comfortable. Somewhere between the 430 degrees of Mercury's sunlit surface and the -180 degrees of its shadowed craters, in the extraordinarily narrow band of temperatures that life on Earth has managed to thrive within, you are resting. Comfortable. Exactly the right temperature. Neither fire nor ice, but the improbable, beautiful middle ground that this planet and its atmosphere and its distance from the sun conspire to maintain. Mercury burns and freezes simultaneously. You are simply warm. And that warmth, that comfortable ordinariness of temperature, is in its own quiet way one of the most remarkable things in the solar system. Rest in it now. Let the heat of Mercury's day and the cold of its night both recede to comfortable distance. Interesting, wonderful facts about a distant world. Not anything that touches you here in the warm dark where you are drifting, slowly and comfortably, towards sleep. Here is your sixth segment, written in the same calm, expansive style and paced for a full 25 to 35-minute listen. Segment 6, Walking the Surface, Geology. There is a particular kind of beauty that belongs to old things. Not the beauty of the new, the bright, the polished, the freshly made, but the quieter, deeper beauty of things that have endured. The beauty of a mountain range worn smooth by 100 million years of wind and rain. The beauty of an ancient tree whose rings record centuries of drought and plenty. The beauty of a stone wall built by hands long gone, still standing in a field, still doing what it was built to do. There is something in age itself, in the sheer accumulated weight of time, that commands a kind of reverence. A recognition that what we are looking at has persisted through more change and upheaval than we can easily imagine, and is still here, still present, still quietly itself. The surface of Mercury is beautiful in exactly that way. It is one of the oldest surfaces in the solar system, a landscape that preserves, in its craters and cliffs and plains and strange, cheese-like depressions, a record of events stretching back nearly to the birth of the solar system itself. A record written not in words or symbols but in rock and impact and the slow, inexorable physics of a cooling planet contracting over billions of years. Tonight we are going to walk that surface together in imagination, moving slowly and unhurriedly across the ancient terrain, pausing to look at the great scar of the Caloris Basin, climbing in the mind's eye to the top of a cliff 3 kilometers tall, standing at the edge of the strange hollowed landscape the scientists call hollows, and feeling beneath our hypothetical feet the slow, patient contraction of a world that has been cooling and shrinking since before the Earth had oceans. It is a long walk, and we are in no hurry. Let your body settle a little more deeply into rest. Let the tension in your muscles dissolve, one group at a time, from your feet upward through your legs and your back and your shoulders and your neck. Let your jaw unclench and your brow smooth. There is nothing to figure out tonight, nothing to plan or worry about or prepare for. There is only the surface of Mercury, ancient and dark and extraordinary, waiting patiently to be described. And you, warm and still, drifting slowly toward the comfortable edge of sleep. Let us begin with what you would see if you could somehow stand on Mercury's surface and simply look around. The first thing that would strike most observers, arriving at Mercury for the first time, is the overwhelming sense of familiarity. Because the surface of Mercury looks, in most respects, remarkably like the surface of Earth's moon. Gray, heavily cratered, ancient and battered and scarred by billions of years of impacts from the debris that fills our solar system, the meteoroids and asteroids and cometary fragments that have been striking planetary surfaces since the solar system was young. The terrain is varied. There are rugged, chaotic highlands where craters overlap craters in a dense, complex mosaic, and there are smoother, flatter plains where ancient lava flows once resurfaced the landscape and buried the older craters beneath fresh rock. There are mountains and valleys and long sinuous ridges and enormous flat-floored impact basins and the remnants of volcanic vents. But above all, there are craters of every size, from tiny pits a few meters across to enormous basins hundreds of kilometers wide. Mercury has been collecting craters for the entirety of its existence, and the surface bears witness to every one of them. The resemblance to the Moon is not superficial or coincidental. Mercury and the Moon are similar in size, similar in their lack of substantial atmosphere, similar in their geological history. Both are ancient rocky bodies that experienced intense volcanic activity early in their histories and then, as their interiors cooled and their geological engines wound down, became relatively inert surfaces exposed to the continuous rain of impacts from space. Both show the record of what is called the Late Heavy Bombardment, a period roughly 4 billion years ago when the inner solar system was subjected to an intense surge of large impacts, probably triggered by gravitational instabilities among the outer planets that sent large numbers of asteroids and comets raining inward. The scars of that period are written all over both Mercury and the Moon, preserved with remarkable clarity on surfaces that have not been significantly reshaped by the erosion and tectonics that have erased so much of Earth's early record. But Mercury is not identical to the Moon. It has its own peculiarities, its own geological features that set it apart, its own strange and beautiful details that make it unmistakably itself. And one of the first of those peculiarities you would notice, standing on the surface, is the darkness. Mercury is very dark. Not in the way that we might use the word casually, not dark the way a shadowed room is dark, or the way a cloudy day feels dark compared to a sunny one. Dark in a precise, measurable, quantifiable way. A planet's reflectivity is measured by a value called its albedo, a number between 0 and 1, where 0 means a surface that absorbs all incoming light and reflects none, and 1 means a surface that reflects all incoming light and absorbs none. Earth's albedo, averaged across its surface including oceans and clouds and land, is about 0.30. It reflects about 30% of the sunlight that hits it. The Moon's albedo is about 0.12. It reflects about 12%. Mercury's albedo is approximately 0.06. It reflects only about 6% of the sunlight that strikes it. 6%. Mercury absorbs 94% of the light that falls on it. To put that in perspective, 6% reflectivity is roughly comparable to the reflectivity of fresh asphalt, the blacktop surface of a newly paved road. Mercury's surface is, in terms of how dark it is, approximately as dark as a parking lot, which makes it genuinely extraordinary that Mercury appears as bright as it does in our sky. It is visible to the naked eye, sometimes quite prominently. But that visibility is entirely a consequence of how much sunlight Mercury receives at its close distance from the Sun. There is so much sunlight falling on it that even reflecting only 6% of it produces a visible point of light. But the surface itself, if you were standing on it, would appear not gleaming or silvery or bright but deeply, consistently dark. A dark gray landscape under a black sky, with the enormous sun blazing above casting hard, sharp-edged shadows onto terrain that drinks in the light rather than bouncing it back. Why is Mercury so dark? This is a question that planetary scientists have found genuinely interesting, and the answer they have arrived at is both surprising and beautiful in its implications. Mercury's surface appears to be darkened, at least in part, by a layer of graphite, carbon in its crystalline form, the same material that forms the lead in a pencil, that coats the inside of a charcoal grill, that makes up the electrode in certain types of batteries, graphite, and the hypothesis, supported by spectral observations from the Messenger spacecraft, is that this graphite layer is not a recent addition to Mercury's surface but a relic of the planet's ancient past. Specifically, it may be the remnant of an ancient carbon-rich crust that formed billions of years ago when Mercury's interior was still largely molten and a global magma ocean covered the surface. As that primordial magma ocean cooled and crystallized, different minerals separated out at different depths based on their density and chemical properties. Carbon, in the form of graphite, is unusually buoyant in magma. It floats. And so as the magma ocean crystallized from the bottom up, graphite may have risen to the surface and formed a dark layer at the top of the cooling crust. Later geological processes, volcanic eruptions, impacts, resurfacing events, buried much of this original graphitic crust under newer material. But those same impacts also mixed material from depth back up to the surface, continuously recycling that dark carbon-rich material and spreading it across the landscape. The darkness of Mercury's surface may therefore be a kind of geological memory, a persistent echo of the planet's earliest history, of the cooling of a global magma ocean more than 4 billion years ago, preserved and redistributed across the landscape by billions of years of impacts. Beyond its darkness, Mercury's surface has some unusual chemical characteristics. Observations and measurements of Mercury's surface composition have found unusually high concentrations of certain elements that planetary scientists did not expect to find in such quantities, most notably magnesium and sulfur. The presence of high sulfur levels on Mercury is particularly interesting because sulfur is what is called a volatile element. It has a relatively low boiling point and tends to be driven off from planetary surfaces by heat. Mercury's proximity to the Sun and the extreme temperatures its surface experiences would be expected to have depleted volatile elements over time. And yet the sulfur is there in higher concentrations than we see on Earth or the Moon or Mars, suggesting either that Mercury formed from material that was unusually rich in sulfur to begin with, or that the volatile elements on Mercury behaved differently during the planet's formation and early history than our models predicted. This is one of several pieces of chemical evidence suggesting that Mercury's formation and early history were more complex and surprising than early theories assumed, and it remains an active area of research and debate in planetary science. Now, let us travel, in imagination, to the most dramatic feature on Mercury's entire surface. The one that stops you in your tracks when you first encounter it. The one that redefines your sense of what an impact can do to a world. The Caloris Basin. Caloris is an impact basin, a vast, circular depression created by the collision of an enormous object with Mercury's surface billions of years ago. It is one of the largest impact structures in the entire solar system. Its diameter is approximately 1,550 kilometers. To help make that number concrete, 1,550 kilometers is roughly the distance from New York City to Miami, or from London to Rome, or from Sydney to Adelaide. If you placed the Caloris Basin over Western Europe, it would stretch from London to well beyond Warsaw. It is a scar on Mercury's face that is, by any human measure of distance, continental in scale. The object that created Caloris, the impactor as planetary scientists call it, was estimated to have been approximately 100 kilometers wide. 100 kilometers. A rock the size of a small country or a large city, traveling at the kind of velocity that objects achieve in the inner solar system, somewhere between 20 and 60 kilometers per second, in all likelihood. The energy released by the Caloris impact is essentially beyond comprehension in everyday terms. It was sufficient to melt vast quantities of rock, send enormous shock waves rippling through Mercury's interior in all directions, throw ejecta. The debris blasted out of the crater thousands of kilometers across the surface and fundamentally reshape the geology of a significant fraction of the entire planet. The floor of the Caloris Basin is covered with a complex network of ridges and troughs, the product of the enormous pressures and temperatures of the impact and the subsequent cooling and settling of the vast pool of molten rock that temporarily flooded the basin floor. It has been compared, in some descriptions, to a cracked eggshell, or to the surface of a cooling lava lake, or to the intricate geometry of a spider's web traced in rock. Later volcanic activity partially resurfaced the floor, covering some of the original impact features with smoother planes. And subsequent smaller impacts have pocked the floor of the basin with their own craters, adding layers of complexity to an already extraordinary landscape. But perhaps the most remarkable consequence of the Caloris impact is not found within the basin itself. It is found on the opposite side of the planet. Because when that enormous object struck Mercury with such extraordinary force, the shock waves it generated did not simply spread outward from the impact site across the surface. They also traveled downward through the interior of the planet, through the mantle and to the core, and then converged at the point on Mercury's surface directly opposite the Caloris Basin. The point on a sphere that is diametrically opposite to any given point is called the antipode. And at the antipode of the Caloris impact, the shock waves from the collision focused and converged and arrived simultaneously from all directions, releasing their energy in a concentrated burst that tore the surface apart. The result is a region of extraordinary, chaotic terrain on Mercury's surface known officially as the chaotic terrain, but more memorably and descriptively as the weird terrain. It is a landscape of jumbled, angular hills and depressions, buckled and fractured and disrupted, that shows no resemblance to any of the geological processes that shaped the rest of Mercury's surface. It looks as though someone picked up the ground and shook it violently, which is, in the most fundamental physical sense, exactly what happened. The antipodal focusing of the Caloris shock waves essentially disrupted and scrambled the surface from below, shattering the crust and heaving the terrain into a confused, chaotic jumble that has no clear structural organization. It is one of the most alien and visually striking landscapes in the solar system, strange and beautiful and deeply unsettling in the way that landscapes created by forces entirely beyond human scale tend to be. The fact that we can trace the weird terrain directly back to the Caloris impact, across 1,550 kilometers of basin diameter, through the entire interior of the planet to a point on the exact opposite side of the globe, is one of those things that reminds you what physics actually is. Not a collection of abstract equations written in textbooks, but the literal operating system of reality. The mathematics of shockwave propagation, working itself out through the body of a planet, producing a strange and fractured landscape on the far side of a world from a single ancient impact. Physics in action at planetary scale, leaving its mark in stone for billions of years. And now let us leave the Caloris Basin and the weird terrain and travel across Mercury's landscape to another extraordinary set of geological features. Features that tell a different kind of story, not the story of a single catastrophic impact, but the slower, longer story of a planet cooling and contracting over geological timescales. Mercury has what are called lobate scarps. The word scarp refers to a steep, cliff-like slope, what you might call an escarpment, a sudden dramatic drop in the elevation of the landscape. Mercury's lobate scarps are cliffs, long, sinuous, dramatic cliffs that wind across the surface in great curving lines, cutting across craters and plains and other geological features without regard for whatever came before them. They are called lobate because their profile, viewed from above, has a characteristic lobed, wavy shape, not a straight line but a gently curving, sinuous trace across the landscape that looks, from orbit, something like a great snake lying still across the ground. These cliffs can be enormous. Some of Mercury's lobate scarps rise to heights of 3 kilometers, nearly 10,000 feet. For comparison, the cliffs of the Norwegian fjords, some of the most dramatic cliff faces on Earth, reach heights of around 1 kilometer. Mercury's largest lobate scarps are 3 times higher than that, and they can extend for hundreds of kilometers in length. Great walls of rock marching across the landscape in slow curves, dividing the terrain on either side at dramatically different elevations. The origin of Mercury's lobate scarps is one of the most geologically interesting aspects of the planet, because they are not the product of volcanism or impact or tectonic forces of the kind that create mountains and rifts on Earth. They are the product of something simpler and more fundamental, the slow cooling and contraction of the planet itself. Mercury, like all rocky planets, formed at high temperatures and has been cooling ever since. As the interior of Mercury cooled over billions of years, the planet shrank. The rocks contracted. The volume of the planet decreased. And when a sphere decreases in volume, its surface area must also decrease. The surface, in a sense, has too much material for the now smaller volume it needs to cover. It is somewhat analogous, in a very rough way, to the skin of a fruit that has dried and shrunk. The skin wrinkles and buckles because there is more surface than the reduced volume beneath it requires. On Mercury, that surface response to contraction produced the lobate scarps. As the planet shrank, enormous sections of the crust were pushed against each other, and one section rode up over another along great thrust faults. Fractures in the crust along which one block of rock was forced upward relative to the block beside it. The result was a cliff, the sharp face of the block that was pushed upward, now towering above the block that was pushed down. And those cliffs have persisted on Mercury's surface for billions of years, preserved by the absence of the erosional forces that would have worn them down on a planet with an atmosphere and water and weather. The total amount of shrinkage that Mercury has experienced over its history is estimated to be approximately 7 kilometers in radius. 7 kilometers. The planet is about 7 kilometers smaller in radius today than it was when it first formed, which means that over the entirety of its history, Mercury has contracted by enough that if you measured from its center to its surface, you would get a number 7 kilometers smaller than the number you would have gotten at the beginning. The surface has responded to that contraction by wrinkling and thrusting, producing the great lobate scarps that wind across the landscape today. And here is something remarkable about those scarps, something that connects Mercury's geological past to its geological present. The lobate scarps are not all ancient. Some of them appear to be relatively young in geological terms, formed within the last few 100 million years rather than billions of years ago, which means that Mercury is still contracting, still cooling, still shrinking, slowly and steadily, even today. The geological processes that formed the lobate scarps have not entirely stopped. Mercury is not a completely dead and geologically frozen world. It is still, by the evidence of its own surface, a world in slow but ongoing geological transformation. This makes Mercury the only other rocky planet in our solar system, besides Earth, that shows clear evidence of ongoing tectonic activity. Not tectonic activity of the dramatic, Earth-like variety, no plate tectonics, no subduction zones, no mid-ocean ridges spreading apart and carrying continents with them. Mercury's tectonic activity is of a different and simpler kind, the slow, contracting kind, produced by a cooling interior rather than by the churning convection of a partially molten mantle. But it is real, and it is ongoing, and it places Mercury in a select and interesting category of active worlds. The ancient volcanic history of Mercury is also written clearly in its surface. Large regions of Mercury are covered by smooth plains, areas where the original cratered terrain has been buried under flows of ancient lava. These volcanic plains, called the smooth plains, are thought to have formed during a period of intense volcanic activity early in Mercury's history, when the interior was still hot enough and fluid enough to drive massive eruptions of lava across the surface. The lava covered the older cratered terrain, flooding the lowlands and the floors of large impact basins, and cooled into the smooth, relatively flat landscapes visible today. In some regions, the smooth plains have subsequently been cratered by later impacts, their original smoothness disrupted by the billions of years of meteoroid bombardment that have followed the period of their formation. In other regions, particularly inside large impact basins like Caloris, the volcanic resurfacing has been so geologically recent, relatively speaking, that the plains retain a relatively smooth appearance with only modest cratering accumulated since the lava flows solidified. The evidence for ancient volcanism on Mercury was, for a long time, a matter of debate. Some early planetary scientists believed Mercury's smooth plains were formed by impact melt rather than volcanic lava. Melted rock produced by the impacts themselves rather than by eruptions from the interior. But the data returned by the Messenger spacecraft, particularly measurements of the surface composition and the detailed topography of the smooth plains, strongly supported the volcanic interpretation. Mercury was, billions of years ago, a volcanically active world. Lava erupted from its interior, flowed across its surface, and reshaped the landscape in dramatic ways. That era has long since passed, as Mercury's interior cooled and the volcanic engine wound down. But the landscape it left behind is still there, still visible, still telling the story of those ancient eruptions to anyone with the instruments to read it. And now let us pause, in our imaginary walk across Mercury's surface, at one of the most recently discovered and most intriguing features of the Mercurian landscape. Features that did not appear in our maps until the Messenger spacecraft began sending back detailed images. Features that were genuinely unexpected and that are still not fully understood. They are called hollows. Hollows are shallow, irregular depressions in Mercury's surface, somewhat like the holes in a piece of Swiss cheese, as some scientists have described them, though that comparison only captures part of their character. They are typically tens of meters to a few kilometers across and relatively shallow, a few tens of meters deep. They tend to appear in clusters, forming pitted, irregular landscapes that look quite different from ordinary impact craters. Their edges are often bright and fresh-looking, not darkened and smoothed by the long accumulation of micrometeoroid gardening that gradually darkens and blends most of Mercury's surface features over time. And they appear to be young, geologically very young, perhaps still forming today. The leading hypothesis for how hollows form involves a process called sublimation, the direct transition of a material from solid to gas, without passing through a liquid phase. On Earth, this is familiar from dry ice, solid carbon dioxide that converts directly to carbon dioxide gas at room temperature without melting. In Mercury's hollows, the proposed mechanism is that the intense solar radiation and the bombardment of the solar wind cause certain volatile materials in Mercury's surface rocks, materials with relatively low sublimation points, to convert directly from solid to gas and escape into the exosphere. As those volatiles escape, they leave behind the overlying rock unsupported, causing it to collapse and form the irregular, pitted depressions we see. The bright appearance of hollows is consistent with this fresh surfaces that have not yet been darkened by the space weathering processes that affect older terrain. The exact composition of the volatile materials responsible for hollows is still being investigated. Sulfur compounds are a strong candidate, given Mercury's anomalously high surface sulfur concentrations. Certain chlorine compounds and other volatile minerals found in Mercury's crust are also possibilities. Whatever the specific material, the hollows suggest that Mercury's surface is not merely a passive, static landscape being slowly worn down by impacts. It is, in places, an actively evolving surface where geological change, driven by the direct action of solar radiation on surface materials, may be occurring on timescales that are short by geological standards. The constant modification of Mercury's surface by smaller impacts is also worth considering as we complete our imaginary walk. Mercury's surface is continuously being altered by the rain of micrometeoroids, tiny fragments of rock and dust, typically no larger than a grain of sand or a small pebble, that strike the surface constantly from all directions. On Earth, the vast majority of these tiny impactors burn up in the atmosphere long before they reach the ground. On Mercury, with no atmosphere to provide that protection, every micrometeoroid strikes the surface directly. The cumulative effect of billions of years of micrometeoroid bombardment is a process called impact gardening, the slow churning and mixing of the uppermost layer of the surface by countless tiny impacts, gradually pulverizing surface rock into a fine powder called regolith. The entire surface of Mercury is covered in this regolith, a loose, powdery layer of fragmented rock, similar in character to the regolith on the Moon, that has been produced and continuously reworked by impacts over billions of years. And those impacts hit harder on Mercury than they would on Earth, even at the same impactor size and initial velocity. Because Mercury is so close to the Sun's powerful gravity accelerates debris in the inner solar system to higher velocities than would be reached by similar objects farther out. Objects falling toward the Sun accelerate as they approach it, gaining kinetic energy from the gravitational field. By the time a meteoroid reaches Mercury's orbit, it has been accelerated by the Sun's gravity to a higher velocity than the same object would have reached at Earth's orbital distance. Higher velocity means higher impact energy, much higher, since kinetic energy scales with the square of velocity. An object striking Mercury hits harder than the same object would hit Earth, for the simple reason that it has been accelerated to a greater speed by the Sun's proximity. We will finish our walk at a feature that is, visually and symbolically, one of the most striking on Mercury's entire surface. A formation called Pantheon fossae, which translates roughly from Latin as the fossae of the Pantheon, the fossae being long, narrow troughs or ditches carved into the surface. Pantheon fossae is a system of long, linear troughs radiating outward from a central point, spreading across the landscape in all directions like the spokes of a wheel, or the legs of a spider, or the comparison that has stuck most firmly in the popular imagination, like a spider sitting at the center of its web. The formation is enormous in scale, spanning several hundred kilometers from one side to the other. At its center is an impact crater, and from that crater, more than 100 long radial troughs extend outward, cutting across the older terrain in straight lines that converge at that central point. The origin of Pantheon fossae is not entirely settled, but the most widely accepted explanation involves the intrusion of magma from Mercury's interior. In this model, magma pushing upward from below caused the overlying crust to fracture along radial lines extending outward from the point directly above where the magma was pushing, producing the spoke-like pattern of troughs that we see. The crater at the center may have formed later, from an impact that happened to hit almost exactly at the center of the radial pattern, or it may have been related to the magmatic event itself. Either way, the result is a feature of extraordinary visual impact. A giant spider, drawn in rock by ancient geological forces on the face of the solar system's smallest and innermost planet, visible from orbit and now known and studied and wondered at by the scientists of a small civilization on the third planet. Mercury's surface is a museum, an open-air museum of planetary history, covering 4.5 billion years of solar system evolution, written in impact craters and volcanic plains and shrinkage cliffs and strange hollows and ancient spider patterns of rock. Every feature has a story. Every crater records a collision. Every smooth plain records an eruption. Every lobate scarp records the slow contraction of a cooling world. Every hollow records the slow escape of volatile elements under the relentless pressure of solar radiation. Every dark patch of graphite records the cooling of a primordial ocean of magma. And the weird terrain, that jumbled, fractured landscape on the far side of the world from the Caloris Basin, records the focusing of shockwaves through a planet's interior, the geological echo of an impact powerful enough to reshape a world. You have walked a long way tonight in imagination, from the dark, graphite-dusted plains to the rim of the Caloris Basin, across the lobate scarps, up the 3-kilometer cliffs and down the other side, through the strange, pitted landscape of the hollows past the spiderweb pattern of Pantheon Fosse, spreading its spokes across hundreds of kilometers of ancient rock, through the weird terrain, buckled and jumbled and haunted by the memory of an impact on the other side of the world. It is a remarkable landscape, old and dark and scarred and strange, but beautiful in the way that very old, very enduring things are always beautiful. Beautiful the way a mountain is beautiful, or a canyon, or a fossil preserved in stone, because it carries time within it, because it is a record that has survived, because it is still here, still legible, still telling its stories to anyone who takes the time to look and to listen. And now let the surface of Mercury recede gently into the background of your mind. Let the craters and cliffs and hollows and spider patterns grow soft and distant, the way a landscape seen from a great height gradually loses its detail and becomes simply texture, and then simply color, and then simply a feeling of oldness and vastness and quiet. You are warm. You are still. The ancient surface of Mercury is exactly where it has always been, dark and extraordinary and patient and alone in its orbit around the sun. And you are here, drifting slowly and comfortably towards sleep, carrying within you the quiet knowledge of a world more fascinating than it appears from the outside, more complex, more beautiful, more alive with geological history than its small and unassuming size might suggest. There is something quietly profound about the idea of an interior, of what lies beneath the surface of things. We spend most of our lives attending to surfaces, the visible, the touchable, the immediately present, the face of a person, the facade of a building, the landscape spread out before us when we look out of a window. Surfaces are what we navigate by. They are the interface between ourselves and the world. And yet the most important things, the things that determine the character and behavior and ultimate nature of something, are almost never on the surface. They are deeper, hidden, requiring patience and ingenuity and the right instruments to find. A person's deepest qualities are not written on their face. The strength of a tree is in its root system, underground and invisible. The character of a river is determined not just by its surface current, but by the geology of its bed and the aquifer systems feeding it from below. And a planet, a rocky, ancient, complicated planet like Mercury, is defined, more than almost anything else, by what is happening in its interior, by the composition and structure and temperature of the layers of rock and metal that make up the vast majority of its volume and its mass, by the deep, hot, dark world of the core, the innermost region, the heart of the planet, where pressures and temperatures reach conditions that nothing on the surface could survive and where processes occur that shape the behavior of the entire world above. Tonight we are going to go deep. We are going to travel, in imagination, downward through Mercury's thin crust, through the mantle, and into the enormous iron heart at the center of the planet. We are going to explore what is there, how we know it is there, why it matters, and what it produces, including something that planetary scientists did not expect to find around a planet this small, something that surprised the scientific community when it was first discovered, and something that turns out to protect Mercury in subtle but important ways from the relentless bombardment of the solar wind. We are going to explore Mercury's magnetic field, its magnetosphere, the invisible but real and consequential shield that this small, dense planet generates from the churning of liquid metal deep in its interior. But first, let us go deeper still. Let us go all the way down. Let yourself settle a little more completely into rest as we begin. Let the thoughts that are still moving at the surface of your mind slow their motion, the way water slows when you move from a stream into a deeper, quieter pool. Let your breathing deepen just slightly, not forced, just natural, finding its own slower rhythm. There is nothing urgent here, nothing competing for your attention. There is only the quiet and the dark, and the story of a planet's interior, unfolding slowly in the comfortable space between waking and sleep. Mercury's interior can be thought of as a series of concentric shells, like the layers of an onion, but made of rock and metal rather than vegetable matter, and separated by differences in composition, temperature, density, and physical state rather than by the simple chemistry of a growing plant. The outermost layer is the crust, the middle layer is the mantle, and the innermost layer, by far the largest, by far the most dominant, by far the most remarkable, is the core. Let us begin at the outside and work our way in. The crust of Mercury is the thin, rocky outer shell, the part that forms the surface we explored in our last segment. The craters and scarps and hollows and volcanic plains that we walked through in imagination are all features of the crust. And Mercury's crust is, in geological terms, genuinely thin. Current estimates, informed by the gravitational and topographic measurements made by the Messenger spacecraft, suggest that Mercury's crust is approximately 35 kilometers thick on average. 35 kilometers. In a planet with a radius of about 2,440 kilometers, a 35-kilometer crust is proportionally very thin indeed, like the skin of an apple relative to the apple's full volume, or perhaps a little thinner than that. For comparison, Earth's oceanic crust is about 7 kilometers thick and its continental crust averages about 35 to 40 kilometers, similar to Mercury's crust in absolute terms, but Earth is a much larger planet, so its crust represents a smaller fraction of the total. Mars has a crust estimated to be between 24 and 72 kilometers thick, depending on location, averaging perhaps 50 kilometers. The Moon's crust averages about 50 kilometers as well. Mercury's crust is thin even by the standards of other small rocky bodies in the solar system, and this thinness is one of the clues that led scientists to understand just how extraordinary Mercury's internal structure truly is. Because beneath that thin crust, something remarkable is happening. Below the crust lies the mantle, the thick layer of silicate rock that in Earth's interior makes up the majority of the planet's volume and is responsible for the convective processes that drive plate tectonics and volcanism. Earth's mantle is enormous, nearly 2,900 kilometers thick, accounting for about 84% of Earth's total volume. It is not liquid, exactly. Under the extreme pressures of Earth's deep interior, rock behaves in complex ways, solid enough to transmit seismic waves but capable of flowing very slowly over geological timescales. Earth's mantle convection is the engine that drives our planet's geology. Mercury has a mantle too, but Mercury's mantle is thin, surprisingly, startlingly thin, given the planet's overall size. While Earth's mantle accounts for the vast majority of the planet's interior volume, Mercury's mantle accounts for only a modest fraction of its interior. The crust and the mantle together, all of the rocky outer portion of Mercury, represent only a relatively thin shell around the overwhelming dominance of what lies beneath. The core. Mercury's core is enormous, disproportionately, almost shockingly enormous relative to the planet's overall size. Current estimates suggest that Mercury's core extends outward from the center of the planet to approximately 85% of the planet's total radius. 85%. Let that number sink in slowly. If you were to draw a circle representing a cross-section of Mercury, and then drew another circle inside it representing the outer boundary of the core, that inner circle would reach almost all the way to the outer one. The core accounts for roughly 85% of the distance from the center to the surface, leaving only 15% of the radius for the combined thickness of the mantle and crust. In terms of volume, the core occupies approximately 42% of the planet's total volume. In terms of mass, It accounts for somewhere between 60 and 70% of the planet's total mass. Nothing else in the solar system looks quite like this. Earth has a large iron core, and it is one of the reasons Earth is as dense as it is. But Earth's core radius is about 55% of Earth's total radius, large, certainly, but not dominant in the way Mercury's core is dominant. Mercury's core is not just large for a rocky planet's core. It is extraordinarily large, so large that it has fundamentally reshaped the character of the entire planet, making Mercury the densest planet in the solar system per unit of uncompressed volume, giving it its remarkable average density, and producing the magnetic field we are going to explore. The core of Mercury is composed primarily of iron, possibly with some nickel and sulfur mixed in, the same general composition as Earth's core, though the details of Mercury's core composition are still being refined as scientists analyze the data returned by spacecraft. Iron is the most common heavy element in the solar system, and the cores of rocky planets tend to be iron-rich because iron is dense enough to sink toward the center during the early hot, molten phase of a planet's formation, when gravity sorts the planet's materials by density in a process called planetary differentiation. Mercury differentiated as all the rocky planets did, and its iron sank to the center, but in Mercury's case, for reasons that are still not entirely clear, far more of the total planetary mass ended up in the core than in the overlying mantle and crust. The leading explanations for why this happened are the same ones we touched on when discussing Mercury's density earlier in our journey. A giant impact early in Mercury's history may have stripped away much of the original mantle and crust, leaving the iron-rich core as a disproportionate fraction of what remained. Or the intense radiation of the young sun may have vaporized lighter surface material, allowing gravity to pull proportionally more of the remaining mass into the core. Or some combination of both processes, along with other factors related to Mercury's formation environment in the hot inner region of the early solar system. The question of exactly why Mercury's core is so large is one of the most interesting unsolved problems in planetary science, and answering it will require both better observations of Mercury itself and a deeper understanding of how the inner solar system formed. Now, we arrive at one of the most important and most surprising facts about Mercury's core: the question of whether it is solid or liquid, or more precisely, which parts of it are solid and which are liquid. Because it turns out that Mercury's core is not entirely frozen and solid, the way a fully cooled, completely crystallized metallic interior would be. At least part of Mercury's core is still molten, still liquid, still, after 4.5 billion years of cooling, hot and fluid enough to flow, and that flow has consequences that reach all the way to the surface and beyond, consequences that were entirely unexpected when scientists first began studying Mercury carefully. The evidence that Mercury's core contains a liquid component came from careful measurements of how Mercury rotates. We discussed Mercury's rotation earlier in our journey: the slow spin, the 59-day sidereal rotation period, the 3:2 resonance with its orbital period. But it turns out that the way a planet rotates depends not just on how fast it is spinning, but on how its internal mass is distributed. A planet with a completely solid interior rotates differently from a planet with a liquid outer layer over a solid inner core. The liquid layer allows the crust and mantle to wobble slightly relative to the deep interior, in a phenomenon called libration. And measurements of Mercury's rotation, extraordinarily precise measurements made possible by radar observations from Earth and by the Messenger spacecraft, detected exactly this kind of libration. The way Mercury wobbles slightly in its rotation is consistent with a planet that has a liquid outer core beneath its solid mantle and crust, and inconsistent with a planet that is solid all the way through. This was, in retrospect, somewhat surprising. Mercury is a small planet, and small planets cool faster than large ones. They have more surface area relative to their volume, and so they lose heat more quickly. The general expectation had been that Mercury's core might have cooled and solidified long ago. leaving a geologically dead world with a fully frozen interior. And yet, the evidence says otherwise. Mercury's outer core is still liquid, still molten iron hundreds of kilometers below the surface, flowing and churning in the dark interior of a planet that has been cooling for 4.5 billion years. The inner part of the core may be solid. Scientists think there is likely a solid inner core at the center, surrounded by the liquid outer core, in a structure similar in principle to Earth's own layered core, though the details differ, but the outer portion of the core is fluid. And that fluid is doing something extraordinary. It is generating a magnetic field. The discovery that Mercury has a magnetic field was one of the genuine surprises of the early era of planetary exploration. When the Mariner 10 spacecraft flew past Mercury 3 times in 1974 and 1975, becoming the first spacecraft ever to visit Mercury, one of the instruments it carried was a magnetometer designed to measure magnetic fields in space. Scientists expected to detect, at most, a very weak remnant magnetic field, a fossil field frozen into Mercury's rocks from an earlier period when a magnetic field might have existed, similar to the remnant magnetism found in some regions of Mars's crust. What they did not expect was an active, ongoing, dynamically generated magnetic field. But that is what Mariner 10 found. Mercury has a real, living, actively generated magnetic field, produced by processes occurring in its interior right now, not a fossil remnant of an ancient field long since extinguished. The mechanism by which planetary magnetic fields are generated is called the dynamo effect, or the magnetohydrodynamic dynamo. It is a process by which the motion of electrically conducting fluid, in a planet's case, liquid metal in the core, generates and sustains a magnetic field. The physics involved are related to the same principles that make an electric motor work. Moving electrical conductors in a magnetic field generate electrical currents, and those currents in turn generate their own magnetic fields. In a planetary dynamo, the initial magnetic field and the flowing liquid metal interact in a self-sustaining loop. The metal flows, generating electrical currents, which generate a magnetic field, which interacts with the flowing metal, sustaining the currents. The result is a stable, ongoing magnetic field that persists as long as the core remains liquid and continues to flow. On Earth, this process is powered primarily by two things: the heat flowing outward from Earth's hot inner core, which drives convection in the liquid outer core, and the gradual solidification of the inner core, which releases latent heat and also changes the composition of the remaining liquid in ways that drive additional convection. The result is Earth's powerful magnetic field, strong enough to deflect the solar wind, strong enough to guide compass needles, strong enough to protect the atmosphere and the surface from charged particle radiation. Mercury's dynamo operates on the same principle, but it is very different in scale and in strength. Mercury's magnetic field is weak. Genuinely, dramatically weak, only about 1% as strong as Earth's magnetic field at the surface. 1%. If you were carrying a compass on Mercury's surface, it would barely respond to the field, not because the field does not exist, but because it is so faint that its practical effect on a compass needle would be almost negligible. The field is real, and it is measurable with sensitive scientific instruments, but it is far too weak to produce the dramatic effects: the aurora, the protection of a thick atmosphere, the robust deflection of energetic cosmic rays that Earth's much stronger field provides. Why is Mercury's field so weak? Given that it has a large, partially liquid iron core that should be capable of generating a much stronger dynamo. This is another genuinely interesting open question in planetary science. One factor is that Mercury's dynamo may be somewhat suppressed. operating in a regime where the convection in the liquid outer core is less vigorous than in Earth's case, perhaps because the heat flow driving that convection is less intense. The detailed internal heat budget of Mercury, how much heat is produced in its interior, how efficiently that heat is transported outward, and how those factors drive the dynamics of the liquid outer core, is not yet fully understood, and understanding it better will be one of the goals of future Mercury exploration. But there is something else about Mercury's magnetic field that is even more puzzling and more fascinating than its weakness. The magnetic equator, the line around the planet where the magnetic field is perfectly horizontal, which on Earth coincides closely with the geographic equator, is offset from Mercury's geographic equator by nearly 500 kilometers. In the northward direction, the center of Mercury's magnetic dipole is not at the planet's geometric center, as it would be for a symmetrical centered dynamo. It is shifted approximately 500 kilometers northward from where you would expect it. The northern and southern hemispheres of Mercury experience different magnetic field strengths. The northern hemisphere has a stronger field, and the southern hemisphere has a weaker one as a consequence of this offset. This asymmetry is genuinely difficult to explain with standard dynamo theory. A magnetic field generated by a simple, symmetrical convective dynamo in a spherically symmetric liquid outer core should not be systematically offset in this way. The offset implies some kind of asymmetry in Mercury's interior, some difference between the north and the south in terms of the structure or dynamics of the liquid outer core, that is producing a dynamo that is itself fundamentally asymmetric. Several theoretical models have been proposed to explain this. One involves a difference in the heat flow through the mantle between the northern and southern hemispheres, which could drive asymmetric convection in the liquid outer core below. Another involves the geometry of the solidifying inner core. But none of these models has yet been fully confirmed, and the offset magnetic equator remains one of Mercury's most intriguing mysteries. A clue about the planet's deep interior that has not yet been fully decoded. Despite its weakness, Mercury's magnetic field does produce a real and measurable effect on the space environment around the planet. It creates what is called a magnetosphere, the region of space around the planet where the planet's own magnetic field dominates over the interplanetary magnetic field carried by the solar wind. Earth's magnetosphere is enormous, extending tens of thousands of kilometers into space on the sunward side and stretching into a long magnetotail millions of kilometers long on the nightward side. Mercury's magnetosphere is much smaller, a modest bubble of magnetic influence that extends only a few hundred to a few thousand kilometers above the surface before the solar wind compresses it back. But small as it is, Mercury's magnetosphere does deflect a portion of the solar wind. The solar wind, that continuous stream of charged particles flowing outward from the sun, encounters Mercury's magnetic field and is partially redirected around the planet rather than hitting the surface directly. This deflection is not as complete or as effective as the deflection provided by Earth's much stronger field, and a significant amount of solar wind does penetrate Mercury's magnetosphere and reach the surface, contributing to the sputtering processes that feed atoms into the exosphere. But the magnetosphere does provide some degree of protection, and its presence shapes the entire electromagnetic environment around the planet in ways that have real consequences for everything from the exosphere to the surface chemistry. And within that magnetosphere, something extraordinary happens regularly. Something that the Messenger spacecraft documented in striking detail during its years in orbit around Mercury. The interaction between the solar wind and Mercury's magnetic field produces structures called flux transfer events, brief, dynamic events where the solar wind's own magnetic field connects with Mercury's magnetic field in a process called magnetic reconnection. When this happens, channels of magnetic flux, tubes of magnetic field lines, can form that connect the magnetosphere directly to the solar wind. And along those channels, charged particles from the solar wind plasma can be directed downward toward the surface in concentrated streams. These structures have been described in the scientific literature and in popular accounts of Mercury's space environment as magnetic tornadoes. The term is evocative and not entirely inaccurate. They are swirling, dynamic structures that funnel plasma from the solar wind down toward Mercury's surface in ways that are somewhat analogous to the way a tornado funnels air from the upper atmosphere toward the ground. They rotate, they twist, and they deliver material from space directly to the planet's surface with concentrated intensity. These magnetic tornadoes can be enormous relative to the size of Mercury's magnetosphere. Some of them are comparable in diameter to Mercury itself, which means they are not tiny, localized phenomena but large-scale features of the planet's entire space environment. The effect of these plasma-delivering magnetic tornadoes on Mercury's surface is real and significant. The concentrated streams of charged particles they channel toward the surface contribute to the sputtering of surface atoms into the exosphere. They bombard the surface with energetic particles that can alter the chemistry of surface rocks. They are one of the mechanisms by which the solar wind, despite the presence of Mercury's magnetosphere, continues to have a direct and powerful effect on the surface of the planet. The magnetosphere is a shield, but it is an imperfect one, riddled with these dynamic, tornado-like structures that open temporary channels through which the solar wind can reach the surface. The entire system, the liquid outer core generating the dynamo, producing the magnetic field, creating the magnetosphere, which then interacts with the solar wind to produce the magnetic tornadoes, which channel plasma to the surface, which drives the sputtering that feeds the exosphere, is a chain of connected processes linking the deep interior of the planet to the empty space thousands of kilometers above it. A chain that begins in the dark, hot, flowing iron of Mercury's outer core and ends in the streaming, dynamic plasma of the interplanetary environment. It is a reminder that a planet is not just a ball of rock sitting passively in space. It is an active, dynamic system with processes occurring at every scale, from the atomic interactions in the surface rocks to the planet-scale dynamics of the magnetosphere and the flow of liquid metal hundreds of kilometers below the surface. And at the center of all of it, at the heart of the chain, the origin point of the magnetic field, the place where everything begins, is the core. The enormous, iron-rich, partially liquid core that makes up 85% of Mercury's radius and the majority of its mass. Sitting in the dark, under immense pressure, at temperatures high enough to keep iron fluid after 4.5 billion years of cooling. Slowly convecting, slowly generating the electrical currents that sustain the magnetic field. Slowly, patiently, quietly doing what planetary cores do, holding the interior together, driving whatever geological and magnetic activity the planet still possesses, and carrying within its composition and structure the record of the planet's formation and the clues to the mysteries of its unusual past. It is the most inaccessible place on Mercury. No spacecraft will ever descend through the crust and the mantle to sample it directly. No drill will ever reach it. No instrument will ever sit inside it and measure its temperature and composition with direct contact. Everything we know about Mercury's core we have learned indirectly, from the way the planet rotates, from the way gravity varies across its surface, from the magnetic field it generates, from the density we calculate for the planet as a whole. We have never seen it, and we will never see it. And yet, in many ways, it is the most important part of Mercury. The part that explains the most, that carries the most information, that connects most deeply to the planet's identity and history. There is something philosophically resonant about that, about the most important thing being the most hidden, about the heart of a world being accessible only through inference and measurement and the patient, indirect work of scientific deduction. We know Mercury's core is there. We know it is vast and iron-rich and partially liquid and magnetically active. We know it is offset in ways that still puzzle us, and that it generates a field too weak to fully understand by current theory, and that it has been sustaining a dynamo for longer than we might have expected given the planet's size. We know all of this not from direct observation but from the traces and signatures and consequences of the core's existence, felt all the way up at the surface and beyond. It is, in its way, like knowing the character of a person not from what they say directly but from the patterns of what they produce, from the reverberations of their inner life in the outer world. Mercury's core speaks to us through the density of the planet, through the weakness and asymmetry of the magnetic field, through the slight wobble of the rotation, through the magnetic tornadoes in the space above the surface. We listen to those reverberations and try to understand what they tell us about what is happening in the deep interior, far beyond any instrument we could place there. Let that image of Mercury's core settle gently into your mind now. The dark, hot, iron-filled interior, the slow flow of liquid metal in the outer core, generating in its quiet, patient convection the magnetic field that reaches all the way to space. The enormous pressure at the center, where perhaps the innermost iron has frozen into a solid ball. The inner core, surrounded by the flowing liquid outer core, surrounded by the rocky mantle, surrounded by the thin crust, surrounded by the ancient, dark, cratered surface we explored last time. Layers within layers, shells within shells. A world that is more than it appears, richer in structure and in activity than its small, dark, unassuming exterior might suggest. You are warm. You are still. Your own body has its own interior, its own heart beating steadily in the dark, its own deep processes occurring without your attention or your assistance, maintaining you and sustaining you through the night. In some small and poetic way, you and Mercury share that quality. The most important things happening in the dark, in the interior, quietly and without fanfare, sustaining the whole. Rest in that thought. Let it carry you deeper into the comfortable dark. The core of Mercury churns in its deep interior, generating its small, asymmetric, ancient magnetic field. And you are here, drifting slowly towards sleep, as deep and as quiet as anything can be. There is something in the human spirit that has always been drawn toward the difficult journey. Not the easy path, not the well-worn road with clear signposts and predictable terrain, but the hard one. The one that requires ingenuity and patience and the willingness to fail and try again and fail again and try once more. The great ocean crossings of the age of exploration. The ascent of mountains that had never been climbed. The first flights in machines heavier than air that everyone said would never leave the ground. Human history is, in many ways, the story of deciding that something is too hard to do and then doing it anyway. Of finding, again and again, that the limits of what is possible are further out than they appeared from a comfortable distance. The exploration of Mercury is one of those stories. It is a story about a destination that is, paradoxically, both very close to us in the cosmic sense and extraordinarily difficult to reach in the engineering sense. A story about spacecraft that had to perform elaborate celestial dances, looping around planets, borrowing gravity like a traveler trading favors, losing speed in a solar system where everything is constantly falling inward, just to arrive at the right place at the right speed to make useful observations. A story about patient scientists waiting years and decades for data that could only be gathered from a handful of spacecraft, most of which spent only hours or days near their target before moving on. And it is a story that is, right now, still unfolding, still in progress, still producing new surprises, still reminding us how much there is to learn about a world that has been visible to the naked eye since the beginning of human civilization. Tonight, as you drift toward sleep, we are going to follow the human journey to Mercury. We are going to trace the engineering challenge of getting there, the history of the spacecraft that have made the trip, and the extraordinary things they found when they arrived. It is a journey worth taking slowly, worth savoring, because it is one of the genuinely great achievements of the space age. Modest in profile compared to the moon landings or the Mars rovers, perhaps, but no less remarkable in the ingenuity it required and the knowledge it produced. Let yourself settle a little more deeply into wherever you are resting. Let your body grow heavier and more comfortable. Let the thoughts that are still active at the edges of your mind slow their motion and grow quieter. There is nothing to attend to right now. Nothing pressing. Only the story of 3 spacecraft and the planet they were sent to find. Let us begin with the problem. Because before we can appreciate the ingenuity of the solutions that engineers and scientists have developed for reaching Mercury, we need to understand why reaching Mercury is so difficult in the first place. And the answer, when you first encounter it, is genuinely counterintuitive. Because the difficulty of reaching Mercury is not what you might expect. You might expect that the problem with Mercury is that it is hot, that the spacecraft has to survive the intense solar radiation at Mercury's distance from the Sun, the blazing heat that drives surface temperatures above the melting point of lead. And that is certainly a real engineering challenge. Spacecraft sent to Mercury must be carefully designed to manage thermal extremes, and we will come to that. But it is not the primary reason Mercury is so hard to reach. You might expect that Mercury is hard to reach because it is small, a small target, difficult to navigate to with precision. But modern spacecraft navigation is extraordinarily precise, and hitting a target the size of Mercury from interplanetary distances is, for a well-designed mission, not the core challenge. The real reason Mercury is so difficult to reach is orbital mechanics. Specifically, the problem of speed. The problem of having too much of it. Here is the situation. When a spacecraft launches from Earth, it inherits Earth's orbital velocity. Earth travels around the Sun at approximately 30 kilometers per second, and anything launched from Earth's surface is moving at approximately that speed relative to the Sun, before its rocket engines even fire. To travel to an outer planet, to Mars or Jupiter or Saturn or beyond, a spacecraft needs to speed up relative to the Sun. It fires its engines to add velocity, moving into a larger, slower orbit that carries it outward to the destination. The outer solar system is reached by going faster relative to Earth. But Mercury is an inner planet. It orbits closer to the Sun than we do, at a lower altitude in the Sun's gravitational field, moving faster in its orbit, 47 kilometers per second, compared to Earth's 30. And to reach Mercury, a spacecraft must slow down relative to the Sun. It must lose a significant amount of the velocity it inherited from Earth's orbit, dropping into a smaller, tighter orbit that falls inward toward the Sun. If it does not lose enough speed, it will fall toward the Sun too quickly, overshoot Mercury entirely, and continue inward past the planet without ever being captured into orbit. Getting to Mercury is not a matter of adding energy. It is a matter of subtracting it. And subtracting energy, losing velocity in a controlled, precise way, is, from an engineering standpoint, more expensive in terms of propellant than adding it. Rocket engines are efficient at pushing a spacecraft in one direction but are very expensive to use for braking. Carrying enough propellant to both launch from Earth and then brake significantly at Mercury requires an enormous amount of fuel. Far more than most spacecraft can carry while still remaining small enough and light enough to launch affordably. The consequence of this orbital mechanics challenge is one of the most surprising facts about inner solar system exploration. It actually takes more energy, requires more propellant, demands more engineering ingenuity to send a spacecraft to Mercury than to send one to Pluto. Pluto, which is roughly 40 times farther from the Sun than Earth. Pluto, which is so distant that sunlight takes more than 5 hours to reach it. Pluto, which for most of human history was not even known to exist. Reaching that remote, frozen, tiny world at the edge of the solar system is, in terms of the energy budget of the mission, less demanding than reaching the planet closest to the Sun. Let that paradox sit for a moment because it is genuinely striking. The hardest planet to reach is the nearest one. The solar system's most expensive destination, in terms of the energy required to get there and successfully orbit it, is the innermost planet, Mercury. This is why, despite Mercury's ancient history of human observation stretching back 5,000 years, we have sent only 3 missions to explore it. 3. In the entire history of the space age, in more than 6 decades of interplanetary exploration, only 3 spacecraft have ever traveled to Mercury. Compare that to Mars, which has been visited by dozens of orbiters, landers, and rovers, or to Venus, which has been visited by more than 40 spacecraft. The difficulty of reaching Mercury, and the expense of doing so, has kept it one of the least visited and least understood planets in our solar system for most of the space age. The engineers and scientists who design Mercury missions have developed a solution to the speed problem, and it is elegant in the way that the best engineering solutions tend to be not brute force but cleverness. Instead of carrying enough propellant to brake directly at Mercury, they use the gravity of other planets to do the slowing for them. This technique is called a gravity assist or a gravitational slingshot. When a spacecraft flies past a planet in the right direction at the right distance, the planet's gravity accelerates the spacecraft in one direction and decelerates it in another, changing its speed and direction without any fuel expenditure from the spacecraft itself. By carefully choosing the sequence of planetary flybys, mission designers can gradually reduce a spacecraft's velocity or increase it depending on what is needed over the course of years, eventually arriving at the target with the right speed to be captured into orbit. For Mercury, the gravity assist trajectories that have been designed are remarkably complex. Multi-year journeys involving multiple flybys of Earth, Venus, and Mercury itself, each encounter carefully calculated to steal a little more velocity from the spacecraft and bend its trajectory a little closer to the one needed for Mercury orbit insertion. These trajectories are a testament to the extraordinary sophistication of modern orbital mechanics calculations, the ability to model the gravitational fields of multiple planets simultaneously and find, within that complex mathematical landscape, the sequence of maneuvers that gets a spacecraft from Earth to Mercury orbit using the minimum possible propellant. With that understanding of the challenge in place, let us meet the spacecraft that have accepted it. The first probe to visit Mercury was Mariner 10. Mariner 10 was an American spacecraft, part of NASA's Mariner program, a series of interplanetary probes that explored the inner solar system during the 1960s and 1970s. It launched in November 1973, a little over 50 years ago, and it became not only the first spacecraft to visit Mercury, but also the first spacecraft to use a gravity assist maneuver to reach its destination. On its way to Mercury, Mariner 10 flew past Venus in February 1974, using Venus's gravity to redirect its trajectory and reduce its speed, the first time this technique had been used in actual spaceflight rather than just in theoretical calculations. From Venus, Mariner 10 continued inward toward Mercury. It made its first flyby of Mercury in March 1974. And what it found, what its cameras and instruments revealed as it swept past at close range for the first time, was a revelation. The cratered, moon-like surface we described in our geology segment. The magnetic field that no one had expected to find. The exosphere of gases clinging tenuously to the surface. The first direct measurements of Mercury's physical environment. All of it flooding back across millions of kilometers of space to scientists on Earth who were seeing this world properly for the very first time. Because of its trajectory and the careful conservation of its orbital energy, Mariner 10 was able to fly past Mercury not once but 3 times. After its first encounter in March 1974, it continued on its orbit around the Sun, looped back, and made a second Mercury flyby in September 1974, and then a third in March 1975. 3 encounters with Mercury in the space of 1 year, each one returning thousands of images and enormous quantities of scientific data about a world that had previously been known only as a point of light in the sky. But Mariner 10 had a limitation that would not be resolved for decades. Because of the geometry of its flybys, the specific trajectories it followed during each encounter. Mariner 10 always flew past Mercury when the same hemisphere was lit by the Sun. The spacecraft's 3 close approaches all occurred when Mercury was oriented in approximately the same way relative to the Sun and to Mariner 10's approach angle, which meant that the images returned from all 3 flybys covered roughly the same portion of Mercury's surface. When all the Mariner 10 data was assembled and processed, scientists had detailed images and maps of approximately 45% of Mercury's surface, nearly half the planet. But the other 55%, the half that happened to be facing away from Mariner 10 during each of its encounters, remained completely unmapped, completely unseen by any human instrument. A blank half of a planet, unknown and mysterious, for decades after Mariner 10's mission ended. Mariner 10 ran out of attitude control propellant in March 1975, following its 3rd Mercury flyby. Without the ability to maintain its orientation in space, it could no longer point its instruments accurately or transmit data reliably, and the mission was ended. The spacecraft continued on its orbit around the Sun, presumably still circling there to this day, a silent artifact of 1970s engineering now tracing endless loops around our star with no one left to listen to it. For 36 years after Mariner 10's mission ended, no other spacecraft visited Mercury. 36 years. The world changed dramatically in that time. Computers went from room-filling machines to devices small enough to fit in a pocket. The Cold War ended, the internet was invented, the Human Genome Project mapped our DNA, and the space age itself underwent enormous transformation. And through all of it, Mercury sat unvisited and half unmapped, waiting quietly in its inner orbit for someone to come back. The someone who came back was Messenger. Messenger, a name that is both a beautiful tribute to the planet's mythological heritage and an acronym for Mercury's surface, space environment, geochemistry, and ranging, was a NASA spacecraft launched in August 2004. Its mission was to do what Mariner 10 had begun but could not complete: to map the entire surface of Mercury, to measure its magnetic field in detail, to study its thin exosphere, its surface composition, its interior structure, its relationship to the solar wind, to answer the questions that Mariner 10 had raised, and to find the questions that Mariner 10 had not yet known to ask. Getting Messenger to Mercury required one of the most complex trajectories ever designed for an interplanetary mission. Because of the energy problem we discussed, the difficulty of shedding enough velocity to be captured into Mercury orbit, Messenger's mission designers planned a 6.5-year journey involving 6 planetary gravity assists before the spacecraft could even attempt to enter Mercury orbit. 1 flyby of Earth in 2005, 2 flybys of Venus in 2006 and 2007, and then 3 flybys of Mercury itself in 2008, 2008, and 2009, each one using Mercury's own gravity to slow the spacecraft a little more and refine its trajectory, while also returning valuable scientific data before the final orbital insertion maneuver in March 2011. That final orbital insertion, the burn that slowed Messenger enough to be captured by Mercury's gravity and placed into orbit around the planet, was the single most critical event of the mission. A 15-minute rocket burn that had to work essentially perfectly. Too little braking and Messenger would fly past Mercury and continue into interplanetary space, the mission over and the decade of work that led to it wasted. Too much braking and the orbit would be wrong. The burn went perfectly. On March 18, 2011, Messenger became the first spacecraft ever to enter orbit around Mercury. After a 6.5-year journey covering approximately 7.9 billion kilometers, a distance far greater than the straight-line distance between Earth and Mercury, Because the trajectory had to wind and loop through the inner solar system, Messenger was in Mercury orbit, ready to work. And work it did. For 4 years, from March 2011 to April 2015, Messenger orbited Mercury, mapping and measuring and analyzing with a suite of scientific instruments that represented the best technology available in the first decade of the 21st century. It carried cameras that mapped the entire surface at resolutions far beyond anything Mariner 10 had achieved. It carried spectrometers that measured the composition of the surface rocks and the exosphere. It carried a magnetometer that mapped the magnetic field in extraordinary detail, revealing the asymmetry and the offset magnetic equator we discussed in our last segment. It carried instruments to measure the gravitational field of the planet in detail, allowing scientists to infer the internal density structure and the size of the core. And it confirmed, beyond any remaining doubt, the presence of water ice in the permanently shadowed polar craters. The images Messenger returned of Mercury's surface were stunning. The first complete global maps of Mercury, the Caloris Basin in full detail, the lobate scarps winding across the terrain, the hollows, discovered for the first time in Messenger data and unlike anything seen on any other world. Pantheon Foci, the great spider-like pattern of radiating troughs, the weird terrain at the Caloris antipode, all of it mapped and measured and photographed from orbit, a complete visual record of a world that had been half mystery for the entire history of human spaceflight. Messenger's mission was extended twice, first by 1 year and then by another, because the data it was returning was so valuable and the spacecraft was still functioning well enough to continue. By 2015, however, the mission was approaching its end. Messenger had been operating for 4 years in the harsh radiation environment close to the Sun, far beyond its original design lifetime. Its propellant was nearly exhausted. Its orbit, which had been slowly decaying due to solar gravity and radiation pressure, had brought it closer and closer to Mercury's surface. And the decision was made, not reluctantly, but with the kind of scientific intentionality that marks the best mission planning, that Messenger's final act would itself be a scientific contribution. On April 30th, 2015, Messenger was maneuvered to impact the surface of Mercury. Deliberately, the spacecraft that had spent 4 years in orbit, mapping the planet, transforming our understanding of the innermost world, making discovery after discovery, that spacecraft was directed into Mercury's surface at a velocity of approximately 3.9 kilometers per second, creating a new impact crater estimated to be 16 meters across in the northern hemisphere of the planet. The crater has been named after the American poet Amiri Baraka. Messenger became part of Mercury, another mark on the ancient surface, this one made not by a random meteoroid falling from interplanetary space but by a machine built by human hands, sent deliberately to a distant world by the curiosity and ingenuity of the civilization that had been watching that world from the third planet since the beginning of written history. There is something beautiful about that ending, something that feels right. Messenger did not simply fail and drift away into space, silent and forgotten. It gave itself to Mercury, added itself to the landscape, became a feature of the planet it had spent 4 years studying. Its final contribution was a crater, one more mark on a surface already covered with the marks of 4.5 billion years of cosmic history. A small mark, a human mark, the newest mark on one of the oldest surfaces in the solar system. And yet the story does not end with Messenger. Because even as Messenger was completing its mission, planning was already underway for the next chapter of Mercury exploration. A mission more ambitious than anything that had come before. A mission involving not one spacecraft but two. A mission designed not by one nation but by two. A collaboration between the European Space Agency and the Japan Aerospace Exploration Agency, the organizations responsible for space exploration in Europe and Japan respectively. a mission called Bepi Colombo. The name Bepi Colombo honors Giuseppe Colombo, an Italian mathematician and engineer who in the 1970s was instrumental in designing the gravity assist trajectory that allowed Mariner 10 to reach Mercury. He was known to his colleagues as Bepi, a common nickname in northeastern Italy for people named Giuseppe, and when the European-Japanese Mercury mission needed a name, it was given to honor the man whose mathematical ingenuity first showed humanity how to reach the innermost planet. It is a fitting tribute. The most ambitious Mercury mission ever launched bears the nickname of the person who first solved the problem of getting there. Bepi Colombo launched in October 2018, carrying within it not one but two separate scientific orbiters. The Mercury Planetary Orbiter, built by the European Space Agency, is designed to study Mercury's surface, interior, and exosphere in extraordinary detail. And the Mercury Magnetospheric Orbiter, built by the Japan Aerospace Exploration Agency, is designed to study Mercury's magnetic field and its interaction with the solar wind, the magnetosphere, the magnetic tornadoes, the plasma environment that surrounds the planet. When these two spacecraft reach Mercury and separate into their individual orbits, they will together provide a comprehensive, simultaneous multi-perspective study of Mercury that no previous mission could match. Two instruments in different orbits, measuring different aspects of the same world at the same time. Getting Bepi Colombo to Mercury requires an even more elaborate trajectory than Messenger's. Because Bepi Colombo is carrying two orbiters and the hardware needed to eventually separate and deploy them, it is a heavier spacecraft than Messenger, and heavier means more challenging to slow down at Mercury. The trajectory designed for Bepi Colombo involves 9 gravity assist flybys in total, 1 of Earth in 2020, 2 of Venus in 2020 and 2021, and then 6 of Mercury itself in 2021, 2022, 2023, 2024, 2024, and 2025. 9 separate close encounters with planets, each one carefully calculated to steal a little more orbital energy from the spacecraft and bend its trajectory incrementally toward the conditions needed for Mercury orbit insertion. 9 planetary dances spread over 7 years of interplanetary travel. Each Mercury flyby, even before Bepi Colombo reaches orbit, has already returned scientific data. Cameras and instruments aboard the spacecraft have been active during the Mercury encounters, photographing the surface from distances of a few hundred kilometers and taking measurements of the space environment. The images returned from Bepi Colombo's Mercury flybys have shown the planet in new detail, complementing and extending the Messenger maps, and scientists have already begun analyzing the data for new discoveries. Bepi Colombo is scheduled to enter Mercury orbit in late 2025. After arrival, it will spend an extended period in a combined configuration before eventually separating into its 2 individual orbiters, each taking up its planned orbit and beginning its dedicated science mission. The Mercury Planetary Orbiter will image the surface, measure composition and topography and gravity, study the interior through its gravitational signature. The Mercury Magnetospheric Orbiter will map the magnetic field in unprecedented detail, study the magnetosphere and its interaction with the solar wind, measure the properties of the plasma environment. Together, they will answer questions that Messenger could not, and almost certainly raise new ones that no one has yet thought to ask. There is a particular quality to the excitement that surrounds Bepi Colombo in the planetary science community. It is the excitement of a return, of going back to a place that has already surprised you once and knowing, with the confidence that comes from experience, that it will surprise you again. Mercury has a record of exceeding expectations, of containing features, the ice, the magnetic field, the hollows, the offset magnetic equator, that were not predicted, not expected, not imagined before the data arrived. Every time we have sent an instrument to Mercury, it has told us something we did not know and shown us something we did not expect. There is no reason to believe Baby Colombo will be different. There is every reason to believe it will find things that will surprise us. And beyond Baby Colombo, beyond the mission currently in transit to the innermost planet, future Mercury exploration is already being dreamed about by scientists and engineers who will spend the rest of their careers trying to make those dreams real. More detailed landers, perhaps, that could touch the surface and analyze the regolith directly. Eventually, perhaps, a mission to the polar regions, to land near the permanently shadowed craters, to sample the ancient ice, to take the temperature of the crater floors, to measure the composition of the materials mixed with the frozen water and determine once and for all whether Mercury's ice carries within it organic molecules delivered by the comets that brought the water, the building blocks, perhaps, of chemistry that could eventually lead to life, preserved in ice on a world most people would describe as the least life-friendly in the solar system. That is, perhaps, still many decades away. The engineering challenges of landing on Mercury's surface are formidable, and the science motivation, while real, must compete with the demands of many other extraordinary destinations in the solar system. The moons of Jupiter and Saturn with their subsurface oceans, the asteroids with their record of solar system formation, Mars with its ancient river channels and the search for biosignatures. Mercury will wait, as it always has, patient in its orbit, carrying its secrets until someone arrives with the right instruments to coax them out. But the journey has begun. It began in November 1973 when Mariner 10 lifted off from Cape Canaveral on a trajectory that would take it past Venus and then past Mercury 3 times in 3 decades worth of surprise and discovery. It continued in August 2004 when Messenger began its 6.5-year winding journey through the inner solar system to become the first spacecraft to orbit the innermost planet. It is continuing right now, tonight, as Baby Colombo makes its long, looping, gravity-assist choreographed way toward Mercury orbit, carrying the hopes and the questions of 2 space agencies and dozens of scientific teams and the accumulated curiosity of a civilization that has been watching this tiny, fast-moving, extraordinary world since a Sumerian astronomer pressed its observation into a clay tablet 5,000 years ago. 3 missions, 3 spacecraft, 1 planet, and a journey that began in the dark of human prehistory and continues tonight, with a spacecraft moving through interplanetary space toward a destination that is hard to reach and endlessly worth reaching. Let that sense of ongoing journey carry you gently toward sleep. The sense that the story is not finished, that there is more to come, that the universe, and our small but determined effort to understand it, is a project that continues regardless of whether any individual is awake to witness it. Baby Colombo is traveling right now. Mercury is in its orbit right now. The permanently shadowed craters are cold and dark right now, their ancient ice undisturbed. The magnetic tornadoes are swirling in Mercury's magnetosphere right now, channeling plasma toward the surface. All of it is happening quietly and continuously, in the dark of space while you drift toward sleep here. You are part of the same universe. The same physics that governs Mercury's orbit and its magnetic field and the trajectory of Baby Colombo governs the rise and fall of your chest, the rhythm of your heart, the slow, comfortable chemistry of a body settling into rest. It is all connected, all part of the same extraordinary, patient, beautiful unfolding of a cosmos that has been in motion for 13.8 billion years and shows no signs of stopping. Rest now. Baby Colombo is on its way. Mercury is waiting, and you have somewhere comfortable and warm to be while all of that continues without you. There is a moment in the history of every newly discovered place when the naming begins, when the first maps are drawn and the blank spaces start to fill with words that come from the languages and the stories and the values of the people doing the mapping. The naming of a place is never a neutral act. It is always, in some way, a statement about what the namers considered important, about what they wanted to remember, about which human achievements they thought worthy of being written permanently into the geography of a world. The names that European explorers gave to the coastlines and rivers and mountains of the lands they encountered tell us as much about 16th century European culture as they do about the geography itself. The names that indigenous peoples gave to those same places, many of which predated the European names by thousands of years, tell us something different and often deeper about the relationship between people and the land they lived on. When we began mapping Mercury, when Mariner 10 returned its first detailed images and scientists found themselves staring at a landscape full of craters and plains and valleys and ridges that needed names, the International Astronomical Union, the body responsible for naming features on other worlds, made a series of decisions about what the naming conventions for Mercury would be. And those decisions were, in the most literal sense possible, beautiful. They were decisions that reflected something about what humanity, at its best, chooses to honor. What we decide is worth remembering when we write names into stone or, in this case, into the ancient rock of the innermost planet. Tonight, we are going to wander through the names of Mercury's landscape. Not through the physical features themselves, we have done that already in our geology segment, but through the words that have been attached to them. The names of the craters and the plains and the valleys and the ridges. The human beings and the lost cities and the languages and the scientists that are now, permanently and formally, part of the geography of another world. It is a gentler kind of exploration than what we have done in previous segments. A quieter kind of discovery, and perhaps, in its own way, the most human kind of all. So let yourself settle into this final segment of tonight's journey with a particular kind of ease. The facts tonight are softer. The images are warmer. We are not dealing with temperatures that melt lead or magnetic tornadoes or the thermodynamics of a planetary core. We are dealing with names. With the names of artists and musicians and writers and composers and architects and the lost cities of ancient civilizations. With the decision, made by a committee of scientists, that the craters of Mercury should be named after the dead who created beauty. Let that idea float gently into your mind as your body grows heavier and your breathing slows. The craters of Mercury, named after those who created beauty. There is something very right about that. Let us begin with the craters. Mercury's surface is covered in craters. We established that in our geology segment, and the image is vivid enough that you will recall it easily. Craters of every size, from tiny pits to enormous basins, covering the ancient terrain in the dense, overlapping mosaic of billions of years of impacts. Each one of those craters that is large enough to warrant a name has been given one, according to a specific and deliberate convention established by the International Astronomical Union. The convention is this: craters on Mercury are named after deceased artists, musicians, painters, authors, and other creative figures who have made significant contributions to the arts and humanities during their lifetimes. Not scientists, not politicians, not military figures or explorers or heads of state or religious leaders. Artists, musicians, writers, painters, sculptors, architects, composers, the people whose life's work was the creation of beauty, in sound, in image, in language, in stone and metal and wood and pigment. The people who looked at the world and found within it something worth expressing, something worth making permanent, something worth offering to others as a gift of understanding or emotion or wonder. Those are the people whose names are written into the craters of Mercury. It is a decision that reveals something important about the values of the scientists who made it. Science is often perceived, from the outside, as a purely rational enterprise, the domain of facts and measurements and equations, separate from and perhaps a little suspicious of the more emotional and subjective world of art and music and literature. But the people who named Mercury's craters understood something that the best scientists have always understood, that art and science are not opposites but partners. Both are attempts to understand the world more deeply. Both require creativity, rigor, the willingness to see what others have missed, the courage to express what is difficult to express. The scientist and the artist are, at their core, engaged in the same fundamental project. And the decision to name Mercury's craters after artists is a recognition of that kinship. A statement, written permanently into the geography of another world, that human creativity in all its forms is worthy of cosmic commemoration. The names themselves are extraordinary. Let us wander through some of them, slowly and unhurriedly, the way you might wander through a museum, pausing at each one long enough to feel something, not rushing to the next. Beethoven. There is a crater on Mercury named Beethoven. It is one of the largest named craters on the planet, approximately 643 kilometers in diameter. A great, ancient impact basin whose floor has been partially resurfaced by volcanic plains and marked by subsequent smaller impacts. Ludwig van Beethoven, the German composer who lived from 1770 to 1827, who composed 9 symphonies, 5 piano concertos, 1 violin concerto, 16 string quartets, and an enormous body of other work that transformed the course of Western music. His name rests on Mercury. On the floor of that ancient crater, in the dark regolith left by billions of years of micrometeoroid impacts, the name Beethoven is formally and permanently assigned. The man who composed his greatest works while deaf, who could feel the vibrations of music in the pianos when his ears could no longer carry the sound. His name is on Mercury. Van Gogh. A crater approximately 100 kilometers wide bears the name of Vincent van Gogh, the Dutch post-impressionist painter who lived from 1853 to 1890, who painted more than 2,000 works in the decade before his death, including Starry Night and Sunflowers and the series of self-portraits that show us his face across the distance of more than a century with an intimacy that photographs of the time could not match. Van Gogh, who sold almost nothing during his lifetime and is now recognized as one of the greatest painters who ever lived, has a crater on Mercury. That ancient, dark, cratered depression carries his name into a future so distant that the language in which this sentence is written may be as forgotten as Linear B or Sumerian cuneiform. Shakespeare. William Shakespeare, playwright, poet, one of the most influential writers in the history of the English language, the author of Hamlet and King Lear and A Midsummer Night's Dream and 35 other plays and 154 sonnets, has a crater on Mercury approximately 400 kilometers wide. Shakespeare, who was born in 1564 and died in 1616, who wrote words that have been spoken on stages on every continent of the earth and in dozens of languages, and who created characters Hamlet, Othello, Falstaff, Macbeth, Prospero, who feel as real to millions of readers as any historical person. His name is written into the terrain of the innermost planet. Tolkien. A crater named Tolkien honors John Ronald Reuel Tolkien, the Oxford professor and author who created Middle-earth, who wrote The Hobbit and The Lord of the Rings and The Silmarillion, and who essentially invented, or at minimum radically transformed, the genre of epic fantasy literature. Tolkien, who spent decades building a mythology complete with its own languages, histories, genealogies, and cosmologies, who imagined worlds of such internal consistency and emotional depth that readers have been losing themselves in them for more than 70 years, has his name on Mercury. On the planet he surely would have found fascinating, the swift one, the messenger, the most ancient and strange of the inner worlds. His name is there in the dark soil of an impact crater, alongside the names of Beethoven and Van Gogh and Shakespeare and so many others. And then there are the names that carry with them a particular quality of warmth and unexpected delight. Geisel. There is a crater on Mercury named Geisel, after Theodor Seuss Geisel, known to the world as Dr. Seuss. The man who wrote The Cat in the Hat and Green Eggs and Ham and O, The Places You'll Go and How the Grinch Stole Christmas. The man whose books taught generations of children to love reading, whose illustrations were instantly recognizable in their exuberant, impossible, lovingly ridiculous style, whose sentences had a rhythm that children absorbed unconsciously and that many adults can still recite from memory decades after childhood. Dr. Seuss has a crater on Mercury. Somewhere on the surface of the innermost planet, amid the ancient basins and lobate scarps and volcanic plains, there is a depression in the terrain formerly designated as Geisel, named after the man who put the cat in the hat and the fish on the dish and the Lorax speaking for the trees. There is something that makes you want to smile about that. Something that captures, in a single fact, the full range of what human creativity encompasses, from the symphonies of Beethoven to the rhymes of Dr. Seuss. Both worthy, both honored, both written into the landscape of another world. And Lennon. There is a crater named Lennon after John Lennon, the English musician and songwriter, member of the Beatles, author of Imagine and In My Life and Come Together and dozens of other songs that have been heard by more people, in more countries, in more languages than perhaps any other songs in history. John Lennon, who was born in Liverpool in 1940 and died in New York City in 1980, who imagined a world of peace with a simplicity and directness that made the idea feel genuinely possible, at least for the length of a song. His name is on Mercury. Lennon crater, on the surface of the planet the Romans named after their fastest god, preserving the name of a man who made music that has outlasted every chart position and every critical assessment and settled into something more durable, into the fabric of the culture itself. Think about what it means for these names to be there on Mercury. When we name a street or a building after someone, the name lasts as long as the street or the building, which is to say, perhaps a few centuries at most before the city changes and the street is renamed or the building demolished. When we name a star after someone, the name is informal, not universally recognized, and carries no official weight. But when the International Astronomical Union officially names a feature on another planet after a person, that name is as permanent as anything human beings can create. Mercury will orbit the Sun for billions of years more. The craters on its surface, protected from erosion by the absence of atmosphere and weather, will persist, essentially unchanged, for those same billions of years. The names assigned to them, recorded in the official catalogs of planetary nomenclature, will persist as long as there is a civilization somewhere to maintain the records. Beethoven crater, Van Gogh crater, Shakespeare crater, Tolkien crater, Geisel crater, Lennon crater. These are names written not in sand but in something approaching permanence. In a small but genuine way, the artists of Mercury's crater names have achieved what artists have always sought: something that lasts. Something that outlasts the individual life, that persists through the centuries, that reaches people in times and places the creator could never have imagined. Beethoven could not have imagined, composing his symphonies in early 19th century Vienna, that his name would one day be formally assigned to a crater on the innermost planet. Dr. Seuss could not have imagined, writing his rhyming books for children in 20th century America, that his name would rest on Mercury alongside Beethoven's. Tolkien could not have imagined, building his mythology of Middle-earth in the evenings after his day's academic work, that his name would join Shakespeare's and Van Gogh's and Lennon's on the surface of another world. And yet here they are, all of them together on Mercury. The full list of named craters on Mercury is long and extraordinary in its breadth and its global scope. It is not a list dominated by European names, or by American names, or by the names of any single culture. It reaches across centuries and continents and art forms to honor creative figures from all of human civilization. There is a crater named Murasaki, after Murasaki Shikibu, the Japanese noblewoman who in the early 11th century wrote the tale of Genji, considered by many literary scholars to be the world's first novel. A woman, writing in Heian period Japan 1,000 years ago, created one of the foundational works of world literature. Her name is on Mercury. There is a crater named Hokusai, after Katsushika Hokusai, The Japanese artist whose woodblock print The Great Wave off Kanagawa is one of the most reproduced artworks in history. Hokusai, who lived from 1760 to 1849 and who continued working and learning and producing extraordinary art until the very end of his long life, famously said that if he had lived another 10 years he might have finally understood how to paint properly. His name is on Mercury, in a crater that happens to also be one of the more prominent and extensively rayed craters on the planet. A relatively young impact surrounded by long, bright streaks of ejecta that fan out across the surrounding terrain like brushstrokes. There is a crater named Chekhov after Anton Chekhov, the Russian playwright and short story writer whose works, including The Cherry Orchard and The Seagull and Uncle Vanya and hundreds of short stories of extraordinary economy and emotional depth, transformed the way literature represented the interior lives of ordinary people. There is a crater named Monet after Claude Monet, the French Impressionist painter who spent decades studying the relationship between light and water and time, who painted the same subjects again and again as the light changed, who created the water lily series in his garden at Giverny while losing his sight to cataracts. There is a crater named Coltrane, after John Coltrane, the American jazz saxophonist whose albums A Love Supreme and Kind of Blue helped define the sound of jazz in the mid-20th century. There is a crater named Neruda, after Pablo Neruda, the Chilean poet whose love poems and political poetry and odes to common objects have been read and translated and cherished across the world for nearly a century. The list goes on, and every name on it is a story, a life, a body of creative work that changed something in the world, that gave people new ways of seeing or feeling or understanding or imagining. All of them now part of Mercury's geography. All of them formally and permanently attached to ancient impact structures on the surface of the innermost planet. Now let us turn from the craters to the other features of Mercury's landscape and their naming conventions. Because the craters are not the only named features on Mercury, and the other naming systems have their own kind of beauty. The ridges of Mercury, those long, sinuous elevated features that wind across the terrain, some of them lobate scarps formed by the planet's contraction, others produced by different geological processes, are named after scientists who studied Mercury. Not artists this time, but the people who devoted their professional lives to understanding the planet through observation and calculation and analysis. The people who pointed their telescopes at Mercury, analyzed its spectrum, measured its rotation, developed the models of its interior, designed the missions that were sent to explore it. Their names are written into the ridges, the raised, enduring features of Mercury's landscape, as a recognition that understanding is itself a kind of creation. That the scientist building a model of a planet's interior is engaged in something worthy of the same permanent commemoration as the artist building a symphony or a novel. There is a ridge named Schiaparelli Dorsum, after Giovanni Schiaparelli, the Italian astronomer who in the late 19th century made careful observations of Mercury and contributed to the long-standing but ultimately incorrect belief that Mercury was tidally locked in a 1:1 resonance with the Sun. His observations were wrong in their conclusion but rigorous and influential in their methodology, and his name is written into Mercury's terrain, a reminder that science progresses not only through correct conclusions but through the patient accumulation of careful observations, even when those observations initially point in the wrong direction. The plains of Mercury, those broad, flat, relatively smooth regions that were created by ancient volcanic activity and that cover significant portions of the planet's surface, are named according to a different and particularly elegant convention. They are named after the word for Mercury in different languages of the world. Not in European languages only. Not in the languages of the cultures that first developed modern astronomy. In languages from all over the world, from Asia, from Africa, from the Middle East, from the Pacific, from the indigenous traditions of the Americas. Because Mercury has been known and observed and named in virtually every culture that has ever looked carefully at the sky, and the plains of Mercury honor that universality of human attention. Suisei Planitia, the word Suisei being the Japanese name for Mercury, derived from the Chinese characters for water and star. Odin Planitia from the Norse tradition, where Mercury was sometimes associated with Odin, the All-Father, though other associations also existed. Tyr Planitia, from the Avestan word for Mercury, used in the ancient Persian Zoroastrian tradition. Sabku Planitia, from an ancient Egyptian name for Mercury. Bud Planitia, from Buddha, the Sanskrit name for Mercury in the Hindu tradition. Each one of these names carries within it a language and a culture and a tradition of sky watching that stretches back centuries or millennia. Each one is a reminder that the act of looking up and noticing that bright, fast-moving point of light in the twilight sky is not the exclusive achievement of any one civilization. It is a human achievement, something that people have done independently, in their own languages and within their own mythological frameworks, on every inhabited continent. When you look at a map of Mercury and see these planes named in Japanese and Persian and Sanskrit and ancient Egyptian, you see something that is quietly extraordinary, a record of the universal human impulse to attend to the sky, preserved in the names of geological features on another world. The sky belongs to everyone who has ever looked up at it. And Mercury, the most visible and the most ancient of the classical planets, was noticed and named and woven into story by virtually every culture in human history. The naming convention for Mercury's plains honors that. And then there are the valleys, the valles of Mercury, those long, linear or sinuous depressions in the terrain produced by various geological processes. The valleys of Mercury are named after ancient cities that no longer exist. Cities that have been abandoned or buried or destroyed, that survive now only in archaeological records and historical texts, that were once centers of civilization and commerce and culture and are now silent, their ruins reclaimed by the earth or the desert or the jungle. Angkor Vallis, named after Angkor, the extraordinary temple complex in Cambodia that was the center of the Khmer Empire from roughly the 9th to the 15th century CE, one of the largest pre-industrial cities in the world, abandoned after a series of droughts and political upheavals, and now one of the great archaeological wonders of Southeast Asia. Arecibo Vallis, named after the ancient city of Arecibo in Puerto Rico, though in this case the naming also carries associations with the Great Arecibo Radio Telescope that was instrumental in the radar observations of Mercury's polar ice. Timgad Vallis, named after Timgad, the Roman colonial city in what is now Algeria, founded by Emperor Trajan in 100 CE and now a remarkably well-preserved ruined city whose grid-planned streets and public buildings are still visible, frozen in archaeological time. The naming of Mercury's valleys after lost cities is, like the naming of its craters after artists, a choice that carries a great deal of quiet meaning. Lost cities are a particular category of human memory. Places that were once alive with the full texture of civilization, with markets and temples and houses and children playing in streets and all the ordinary complexity of human life, and that are now silent, emptied, returned to the earth. They are reminders of impermanence, of the fact that even the greatest human achievements in terms of organized civilization are subject to the same entropy and dissolution that affects all things. And yet they are also reminders of persistence, because those cities, though abandoned, survive in memory, in the records of archaeologists and historians, in the literature and art of the cultures that built them, in the ruins themselves, and now in the names of valleys on another planet. Angkor at its peak in the 12th century CE may have been home to as many as 1 million people. 1 million people living in a city in the jungle of what is now Cambodia, building temples of extraordinary architectural sophistication, maintaining a complex society with irrigation systems and trade networks, and a rich tradition of art and scholarship. And now the jungle has reclaimed much of it, and visitors walk through the ruins with the same quiet wonder that surrounds any encounter with an abandoned place. Angkor Vallis on Mercury carries that name and carries with it, in some small way, the memory of all those people and all that complexity, written into the geology of the innermost planet. There is a theme running through all of these naming conventions, if you look at them together. The theme of memory, of the human impulse to remember, to take what was once alive and active and present and to give it a form that can outlast the moment. Art is a form of memory. Music is a form of memory. Literature is a form of memory. Science is a form of memory. A systematic way of accumulating and preserving knowledge across generations. And the naming of features on other worlds is, in its own way, a form of memory too. A way of saying that these people existed, that these cities stood, that these cultures looked at this planet and gave it a name in their own language, and that we think it matters to remember. Mercury, the messenger planet, the planet named after the god who carried communications between the divine and the mortal, carries on its surface the names of an extraordinary range of human achievement. The craters of the artists, the ridges of the scientists, the plains named in the languages of civilizations scattered across the world, the valleys named after cities that once stood and now stand no longer. It is a kind of library written in impact craters and volcanic terrain instead of books. A library of names that spans human history and human geography and every form that human creativity has ever taken. And there is something quietly moving about the idea that these names are there on Mercury right now, that somewhere in the dark regolith of Beethoven crater, the atoms that form that ancient ground have been formally associated with the name of a man who composed symphonies while deaf. That in the smooth volcanic plain of Suisse Planitia, the word for Mercury in Japanese is written into the map of another world. That the ruins of Angkor, abandoned and reclaimed by the jungle of Cambodia, nevertheless persist in the name of a valley on the innermost planet. That Dr. Seuss, the man who rhymed about ham and eggs and cats in hats, has a crater beside Beethoven's. It is all there, all of it formally and permanently part of Mercury's geography. And perhaps, in some small philosophical sense, the naming of Mercury's craters after artists is the most fitting tribute possible to the relationship between science and art. Science sent the spacecraft. Science built the instruments. Science mapped the craters. And then science stepped back and said, these craters should carry the names of artists, of musicians and writers and painters and poets and storytellers. Because the exploration of the universe is not a purely technical achievement. It is a human achievement, and human achievement at its best belongs to all of us, to the engineers and the mathematicians and the astrophysicists, yes, but also to the composers and the novelists and the painters and the people who put rhymes into the mouths of children and made them love words for the rest of their lives. Mercury carries all of them now, on its dark, ancient, cratered surface, under the black sky and the blazing enormous sun. The names of human creativity are written in the terrain of another world. Beethoven and Van Gogh and Shakespeare and Tolkien and Lenin and Geisel and Murasaki and Hokusai and Chekhov and Monet and Coltrane and Neruda and so many others. All of them together, their names resting in the ancient rock, patient and permanent and quietly extraordinary. Let those names drift through your mind now, softly and without any need to hold on to them. The musicians and the painters, the writers and the poets, the lost cities named in the valleys, the languages of the world named in the plains, the scientists named in the ridges. All of it together, a great accumulated human library written into the geography of the planet closest to the sun. Let it all grow soft and warm at the edges of your mind, the names becoming sounds, and the sounds becoming something close to music, and the music becoming the comfortable, familiar feeling of drifting, of letting go, of being carried gently by the current of a voice in the dark toward the quiet country of sleep. Beethoven crater is on Mercury, in the dark, under the black sky. Lenin crater is on Mercury, in the ancient rock, patient and still. Angkor Vallis is on Mercury, carrying the memory of a city that once held 1,000,000 lives. Suisse Planitia is on Mercury, named in the Japanese word for the planet, a word that means water star. And you are here, warm and breathing and still, drifting, letting the names of things become simply sounds, and the sounds become silence, and the silence becomes sleep. That is where we are going now. That is where we have always been going tonight, through all these segments and all these facts and all this extraordinary story of the smallest and innermost and most ancient and most surprising planet in our solar system. Rest now. The names are on Mercury. The craters hold their artists. The plains speak their languages. The valleys remember their lost cities. Everything is exactly as it should be. Sleep now.